Good afternoon, everybody. Can we please take our seats? Sorry? Hello, everybody. Can you please take your seat? Because before we can start this exciting conference, we do have a security video for you guys.
Welcome to Esrin. In the unlikely event of an emergency, any kind of emergency, you can report it to the security team from any internal phone by dialing 3333. From an external phone or a mobile, please dial +39 069 418 0333. Emergency numbers and a site map can be found on the leaflet you were issued along with your security badge. Ignoring it is at your own peril. In case the building needs to be evacuated due to fire or any other kind of emergency, please follow your ESA host to the nearest exit. If you lose your way, follow the exit signs. To leave the building, do not use the lifts, only use the stairs. During the evacuation, refer to Esrin security guards and local area coordinators for advice. Once outside, move towards one of the 4 external meeting points on site. Do not return to any of the buildings until the all clear is given.
Okay, so hello everybody, hello again. My name is Inge Jonkere. I'm the head of the Green Solutions Division. I'm just new in ESA, so also very pleased to meet you. And I have the honor to open this exciting conference, Agriculture Under Pressure. We have the challenging task to have almost 10 interventions in a bit more than 2 hours. So I'm going to have to ask that all the speakers will stick to their time. And I have the honor to introduce Rune Flobbergaven, who's the head of the Climate Action, Sustainability and Space Department. Rune?
Yes, thank you. Thank you very much, Inge. And there are lots of more seats in the front, as you can see, so don't be shy. It feels like there's a bit of gap between the speaker and the main part of the audience. So it is my pleasure, on behalf also of the head of establishment and the director for Earth observation programs at ESA, Simonetta Cheli, to welcome you all here in Esrin. Esrin is for sure the headquarters for Earth observation at ESA, and we like to think of this site also, if not as the headquarters, then at least as one of the main establishments for Earth observation Europe-wise and even on the global scene. Yeah? Lots and lots of the activities that we carry out in ESA are linked to the Earth observation program in Europe, which is second to none, are actually managed from this site. So for those who do not know Esrin very well, I encourage you to take a look around and also talk to our colleagues and find a little bit out what is actually happening here on site. Now, the topic of this workshop, Earth observation for agriculture under pressure, I think is extremely timely. What we are going to talk about is ways to produce more food or increase let's say, dealing with increased population, how we can produce safe food for everybody, accessible and affordable food, and also sustainable use of resources in achieving so. Yeah? So low carbon footprint is one of the things, but also other ways of reducing negative footprint on the environment in general. Nitrogen, for example, is obviously one of the key parameters here. So we at ESA, we are engaged in a lot of activities actually that deal with agriculture and support precisely the topic of this workshop, together with our co-organizing organizations, obviously. They will be presented also during the course of these days. But obviously what is characterizing the ESA program is that we work with a variety of stakeholders, so policy holders or policy owners, also insurance companies, to some extent the whole, let's say, Agri business, or Copa Cogeca, or this kind of organizations, and even to some extent that individual farmers start to get in touch with us. So we do believe that space can make a difference for everybody, and we see that basically all the time. On top of that, in our program at ESA, there is a growing focus on policies in general. Yeah, there is a lot of policy linked to agriculture, obviously. Well, you can go from big to small, talking about CAP, talking about the Green Deal, farm to fork. There's a lot of activities here, also geostatistics, nature restoration, many, many things to which ESA is active. And what we see is a growing focus on this type of activities in the applications programs, but not only at ESA. What does it mean? It means that a lot of the things that used to be the last mile and what we can do with actually become the first mile and the real driver for everything that we do. So it might very well be that we will see, and you will see, in particular after the next so-called ministerial conference at ESA, even stronger focus on this application domain. Maybe one final topic before I will give the floor back to Inge, is that one thing that truly characterizes ESA's activities in Earth observation in general, for climate, but for science, but for everything that we do, and certainly also for agriculture, is the focus that we put on the quality of the data, the veracity and quality characterization of the data. And this is maybe the boring part of the Earth observation program, but is a fundamental part of the program. And you will see that throughout the presentations that we will give here, but certainly also in the future, because we know that there is a lot of not so verifiable data out there. Meanwhile, we talk about fakes entering into the system, and if fake data also start to enter the policy domain, we are all be lost. So one of the things that we are really considering is a program which is really focusing on the role of ESA as a kind of unbiased partner in assuring the quality of all the information that will be used by services like the ones that you are representing. So with that, I think my few minutes are over. I wish you a great time here. The weather is fine. The restaurants are also open in the evening, and there will be plenty of good occasion to talk and have a fruitful workshop. I wish you good fun, great discussions, and again, welcome to Esrin.
Thank you very much, Rune. So then we go to the workshop objectives and organization, and it's Espen Volden who will present. Espen.
Yes, good afternoon, everybody. So I will tell you a little bit about background objectives and about the organization here on behalf of the organizing committee of this workshop. If I can move to the next slide. Yes. So first, for the background, we are not starting today. We have had several workshops in the past here in Essen related to agriculture. In 2020, we had a workshop with the same name as today. And if you go to the website that you can see here, you can also find some summary and recommendations from this workshop. And I would recommend you to have a look at them also tonight in the hotel room. It's good to have them in mind for the rest of the week when we are looking at recommendations again. It's not very quick. So this was just an example from this last workshop. We had a number of different recommendations in different themes. And you can see here, for example, we had recommendations of monitoring different kind of stressors and the climate adaptations. And one result from this recommendation is one follow-up is that we launched a project on this subject. This is called EO for Zero Stress. And this is just one example. We have several activities that were started as results of this recommendation that we received. And just here, these were some general recommendations from last time. One is to do further coordination by institution funding EU R&D. And we have really increased our cooperation between ESA and the Commission, particularly RTD, where we have a joint initiative on Earth system science. Another general recommendation was to coordinate activities that this is really needed. And we are, at the end of this week, on the Friday, we are launching the ESA Science Cluster on Agriculture, which is really a way to make different projects work together, ESA project, but also at the start with projects from Horizon Europe. And one last comment or recommendation last time was that it's useful to have regular EU for Agriculture community gatherings. So that's, you can see today that we have followed this up. So what are the objectives of this workshop that we will have now from today to Thursday? Is first of all to gather the community. This was something that we were not able to do in 2020 because of COVID, so it was all online. It's to present and discuss the state of the art. Also to identify main EU research challenges that can support sustainable agriculture under pressure. And then finally, to provide recommendations to guide future R&D activities of ESA and the Commission. And for the first objective, I think we are quite good in achieving it already, because for gathering the community, we already have close to 300 registered participants from 43 countries. So even if all the seats are not full yet, I think they will be fuller during the week. This is the program. So I just wanted to highlight a couple of things. We will have coffee breaks just outside here in the tent, both in the morning and in the afternoon. And we'll also, at the same place, there will also be a welcoming coffee half an hour before the session starts in the morning. We will have a lunch break every day in the canteen, so we have to move over to the canteen. And just to say that, okay, we finished the last session before lunch at 13:30 or 13:40, and you can go then just to the canteen, but if you stay a bit more, if you're a bit slower, be sure that you're in the canteen at least before 14:30. At that time, you must be queuing to pay. If not, you will not get your meal. Then we have 10 different scientific sessions, 1 hour and a half each. We have 6 different panels, 1 hour each. We have poster sessions, both today, from 6 to 7 today, and also same on Wednesday. And we also have some demos that you will find inside the tent at the end of this, at the end of the tent. We have a couple of demos on the Agriculture Virtual Lab and the Food Security app. And then finally, I would like to highlight that on the Thursday evening, for those of you who can stay until Thursday evening, there will be an event from 5 to 6:30, where we will have lightning talks of a number of ESA projects and ESA projects, where many of them were not presented during the workshop. So finally, I will just give you some house rules that I would ask you kindly to stick to, which is to remain around the designated event areas when possible, to wear your lanyards all the time so that you can be identified by the security. If you need a taxi, you can get it from the registration desk. It's best to do it a couple of hours beforehand. And please also, when you have something, some waste, try to identify the correct bin for it, since we're trying to sort the waste here in Esrin. And the last thing I would like to say is to the speakers that well before your sessions, that you come with your presentation to the Regia at the end of the room here, so that we can get it uploaded well before the session starts. So with that, I will thank you and hand over to Inge again.
Thank you very much, Espen. So it's also clear if you have other questions, please talk to Espen, who is from the organizing committee. So with that, we're going to now connect remotely because we do have some interventions from the European Commission, and we're going to start with DG GRC, Alessandra Zampieri, the Director of Sustainable Resources at the GRC.
Thank you very much, Inge.
Please,
Thank you very much, Inge, and greetings from my side also to all participants, esteemed colleagues, and the distinguished guests. I am the Director responsible for Sustainable Resources at the Joint Research Center of the European Commission, and our role, our mission, is as the science and knowledge service of the European Commission is to inform EU policy making with independent scientific advice and expertise. And we do this in many areas, including, of course, agriculture, and I will move to agriculture in a second. But first, I wanted to say that we do this with three important tools. First of all, with our science. And this conference is very important for us as co-organizers to learn more and to make science advance in this field of agriculture and in this moment of agriculture under pressure. Second, we do it through our dialogue with policy making. We have a knowledge center on Earth observation here at the Joint Research Center in the north of Italy, close to Lake Maggiore, where we put policymakers and scientists together. And through this dialogue, we make sure that science serves policy making. And with the 15 Directorate General participating in this exercise, and you will hear from colleagues speaking after me today, we have at least 3 of the DGs present. We also ensure that science is used where it is needed to best serve policies and produce actionable tools. And third, we do it through our networks. And that's why we are so happy to be here today, because ESA is an important partner for us, but also all of you. You have probably interacted with my colleagues already in the past on the topics of Earth observation or agriculture. And I immediately invite you to also engage with them. They are present in the room, and we really count on the dialogue because this is so important for us, for our work. I said that the JSC has a long history of research and development in Earth observation and its application in the agriculture sector. In fact, we conduct high-quality independent research that not only supports EU policy, but also drives technological advancements. And we place a strong emphasis on the foundational role of basic research, which we often translate into long-standing research lines and operational programs. As I said, this approach ensures that the scientific discoveries and innovations continuously inform and enhance operational systems used in agriculture monitoring and environmental management, thereby extending the impact of our research behind theoretical exploration to practical real-world applications. And we have very good examples. One of these key examples is the development and oversight of comprehensive agriculture monitoring systems. We have been instrumental in designing and deploying sophisticated monitoring systems that guarantee effective implementation and low error rates of policy implementation, such as for the CAP subsidies control. For over 3 decades, the Joint Research Center has been at the forefront of supporting the implementation of the Common Agriculture Policy by providing Member States with essential guidance and innovative tools. And this support has been pivotal in ensuring effective and efficient policy execution across the EU, especially to lower the error rates for CAP control to marginal values. The role of Earth observation in transforming the CAP monitoring has been significant. The transition from traditional on-the-spot checks to comprehensive area monitoring system exemplifies this shift. Enabled by the deployment of the Copernicus program, Earth observation technologies now allow for continuous monitoring of agriculture parcels with increased accuracy and efficiencies of agriculture compliance checks. The methodologies developed through CAP monitoring are not only confined to agriculture compliance, but have broader application across various land management policies. And these vary from climate action, carbon farming, LULUCF, monitoring, reporting, and verification methods. And these expansions underscores the versatility of Earth observation technologies in addressing a wide range of environmental and policy challenges. Other systems were developed for an effective management of agriculture markets and for food security monitoring. The Mars Monitor Agriculture Resources project, which was initiated in 1992, alongside the ASAP, the Anomaly Hotspot of Agriculture Production, provides vital, timely information for crop yield forecast and monitors agricultural resources. These projects support EU policy decisions by offering market transparency and early warning for production anomalies that could affect food security. And both play critical roles in supporting global initiatives like GEOGLAM. We also operate the Copernicus Land Service, which provides detailed data, very important, we heard about data before, and land cover changes, which is crucial for environmental monitoring, urban planning, and emergency management. And this service allows to gain comprehensive and multidimensional insight into land use dynamics across Europe and well beyond. Now, colleagues, I leave you with these words, just invite you to collaborate and engage with the Joint Research Center to contribute actively to this conference, and looking forward to continue our collaboration further. And with this, I wish you a very successful conference, and I give the floor back to you. Thank you.
Thank you so much, Alessandra, for your intervention. And so now we move on to EG DEFIS because of time constraints. So we're going to give the floor to Dr. Mauro Facchini, who's the head of Earth observation at DG DEFIS.
Yes, thank you very much, and good morning. And I think that Franz should have spoken before me, but as I have another commitment starting at 2 by the way, meeting your director, Simonetta Cheli, I really thank you for swapping the presentation. So I'm very happy to be here, even if it's not present, but to speak to this audience in Frascati, and also about this important topic. For those who don't know me, I'm Mauro Facchini, so I'm in charge of the Copernicus program, and as such, I'm very proud to say that a lot of activities that are run by Copernicus in partnership with ESA, but also with the cooperation with the JRC and other entities, are done in support of agriculture. So Copernicus, first of all, 2 messages, is user-driven, and second message is operational. So this is very important in order to provide data that can be used for sustainable activities. Support to DG Agri has been increasing in the last period. DG Agri is a master of EU agricultural legislation, and it has also been integrated in pieces of legislation, in particular the Common Agricultural Policy, and at the same time with other Directorate Generals of the European Commission that are running some policy making, like DG Environment, for example, in the field of deforestation, which has also clear agriculture orientation. But we are working on EU legislation. At the same time, we're also trying to understand how we can better cooperate in an international level. And for this reason, we support the GEOGLAM activities, and most probably my colleague from the GRTD later might expand on that, and also with FAO. As I said, Copernicus is operational because it's running on existing satellites. I imagine that all of you know the Sentinel satellites. Some of them are very much linked to agriculture activities. I'm saying about Sentinel-2 and Sentinel-3 optical satellite, but also radar satellites like Sentinel-1 are more and more used in support of agricultural needs. We are also looking into expansion to new satellites, and some of them have a clear link to what our agriculture needs. And here I'm thinking mostly about 2 new expansion missions. Is the LSTM, so it's a thermal satellite, and then the Hyperspectral CHIME mission that will have several bands that could help me to better understand some agriculture needs. Copernicus has a full open and free data policy, so the data that are generated are made available to everyone, scientists like other users. And in order to improve that, we are setting more and more in place platforms that could make this data available. And in this respect, we have started, or we have established a platform that is much better than in the past, that is called the Copernicus Data Space Ecosystem, that it should be one reference hub where to download the data, not just from the Sentinels, but also from different Copernicus services. Indeed, when we speak about Copernicus services, the first one that is coming to the mind, and when linking to agriculture, is the land one. But at the same time, there might be areas by which also other services, like, for example, the climate or the atmosphere or the emergency, might have some interest to the agriculture area. But as any operational program, it has to evolve, and evolution is based on research. So indeed, we very much support the fact that we have to understand how research should support that, and in which areas this has to be further focused. And these kind of meetings like today are very important to try to understand if what we are doing is good, if what we are doing is enough, or if something more has to be done, and in which areas we have to further explore and research. As mentioned by Alessandra, we have also Knowledge Center on Earth Observation, and one of the mandates of this Knowledge Center on Earth Observation is to set up a strategic research and innovation agenda, meaning to try to understand the areas where Earth observation might need further research that should be financed and support operational activities for the future. I will not take more of your time, and I would like really to encourage to go further in that and to really have an excellent meeting for today. Thank you very much.
Thank you very much, Mr. Facchini. Then we go to Franz Imler, who's the head of the Environmental Observation Sector at DG RTD. Franz, the floor is yours. And sorry for swapping.
You hear me? Yes.
Yes.
Thank you very much. So yes, I work in DG RTD. I'm the head of the sector for environmental observation. I think we work very closely with ESA on the Earth System Science Initiative that Espen has already mentioned. So I'd like to welcome everybody in this workshop that we have co-organized, in particular with my colleague Pascalis Tsiastas, as in the organizing committee. Unfortunately, we cannot be with you these days because we are very limited in our human resources and even more limited in our traveling resources. So I really apologize for that. It would be nice, but it's not possible to be with you. Anyway, as Espen already mentioned, that's very impressive. This workshop brings together more than 300 scientists from all over the world, including some from EU-funded projects. And I hope you will present your achievements, but also in particular to join your forces to help tackling the challenges that we are facing in the agricultural sector using Earth observation. So the EU as a member state has built an impressive capacity in Earth observation, and Mauro already mentioned the Copernicus system with its services, and there's also other systems that are quite useful. And we really want to see these systems being valorized for improving food security and more sustainable food production and agricultural sector. The sector is indeed under pressure as it needs to serve partly conflicting goals, like providing on one hand affordable and healthy food to a growing global population. At the same time, we wanted to contribute to climate change mitigation, to biodiversity preservation, very important because agriculture plays a big role there, to pollution goals, zero pollution, and other policy goals that are formulated, as you probably know, in the European Green Deal policy, which of course is somehow controversial, and we've seen the farmers in Brussels quite impressively demonstrating against or for some issues that they are facing. That was indeed quite an impressive occurrence here with I don't know how many thousands of trucks So how can Earth observation help in this area? And how can the research programs that we run at the EU and also that you run at ESA, how can this help? Well, Alessandra already mentioned a few things. So indeed, we can use these tools to, for example, support precision farming and help making more optimized use of pesticides and fertilizers to optimize crop yields. At the same time, we can use them to monitor environment, to evaluate the impact on the environment, and so also to support the performance, or to optimize the performance, the environmental performance of the farming business. So towards those ends, the European Commission joined forces with ESA in this collaboration that I already mentioned, the Earth System Science Initiative, which also includes the area of agriculture. Probably hear more about this, and you will probably hear more about it during the coming days. We also put together or launched a partnership, a co-funded partnership called Agriculture of Data, that is really there to enforce the use of data, including Earth observation data, in the agricultural sector. It will provide quite significant financial resources for research, for making use of these data, integrating this data. It's very crucial to not only look at Earth observation alone, but really integrate all data that is available, including from, for example, machines on farms, to optimize the practices and to support the agricultural sector in Europe. We are also engaging with GEO, and GEOGLAM was already mentioned also by Mauro, by Alessandra. And we also have a EuroGeo initiative, which brings together the European contributions to GEO, where there's an action group on agriculture that really supports also this collaboration in Europe. And we will have a workshop of the EuroGeo initiative in Krakow in October this year, and I hope to see some of you there. So with this, I really hope that you will have an interesting workshop, inspiring new insights, dialogues with your colleagues that should really lead to more cooperation within our projects, the EU-funded ones, ESA ones, other ones, and with the end goal, of course, to really support the implementation of policies, support the farming sector for more productive, more competitive, and in particular, more sustainable agriculture. Thank you very much, and see you hopefully one day.
Thank you very much. So we go to the DG Agri now with Ursula Frison-Somogyi, who's the Deputy Head of Research and Innovation.
Thank you very much. Thank you very much for the invitation. And yes, unfortunately, I cannot be there either for the same reason than RTD. But it's also very nice to be there remotely. And I will try to complement the interventions that has been made by my colleagues before. Yes, I am in DG Agri, and I am not in the policy unit. I am in the research and innovation unit, so I will focus my intervention on what we do under research. As you said already previously, we haven't started yesterday, so we have already so many good results and an ongoing very good cooperation with different services, and we are used very much in our work Earth observation. Many of you have mentioned agriculture under pressure. I would also say that we are, and the farmers are evolving in a changing context, but there are challenges, but we also have opportunities. And of course, digitalization is part of the opportunities that now are present and that can help our farmers to adapt, to be more resilient, and to gain sustainability. So I would say the two parts of the coin, and we have many opportunities on the sector and also for farmers. So as I said, we have already invested considerably in research and innovation previously, and also in capacity building, which is key to be able to effectively deploy the innovative solutions. And in DG Agri, we are also dealing with different instruments. And especially in our unit, we are dealing mainly with Horizon instruments, but not only. We are also involved in Digital Euro program. And also we are using and making leverage of what we do under Horizon under the Common Agricultural Policy. So there is a cooperation between different policy instruments to be able to make the impact on the ground, which is our objective, to make this sustainable turn. And what we have done under Horizon 2020 and Horizon Europe is to support research and innovation activities to lay down the ground for digitalized and data-empowered European agriculture in rural areas. And I will give you some examples and some data about what we have done so far. And I hope that in the room you have several of the projects present and they will be able to share experiences. And I am very much looking for the outcome that has been objective, that has been set at the beginning of the meeting, to identify the research challenges and to provide recommendation for future research. So I hope that this event will help us also on that. And for that, I will just feed the discussion with some example of what we have done so far. So we have several Horizon Europe funded projects with the EU contribution of more than 100 million euros for developing innovative digital solutions covering, for instance, Internet of Things technologies, automation, robotics, and decision-making support. Through the application of data technologies such as artificial intelligence, big data sets, can be further capitalized, for example, decision-making support tools for farmers, as had been already mentioned by Franz just before me. And I would like to mention three projects: the Crack Sense projects, the Added Value, and the Scale Agri-Data projects, with a contribution of 22 million euros. And they deal with on-farm and Earth observation data for monitoring agriculture and environmental performance. What has been said by Franz before, it is the connection between different tools, so to have the decision-making process of farmers, of policymakers. Another example is the project TEROS, which uses several technologies, including Earth observation, photonics, machine learning, and data fusion techniques for large-scale monitoring and verification of organic farming practices. And with TEROS, other projects such as Stella, Cerberus, and Forset, working on digital technologies for early detection of plant health issues and plant territory surveillance, are part of the cooperation between ESA and the Commission. The collaboration between ESA Agriculture Science Cluster and this project is being actively fostered. And I'm happy that the launch and the first meeting of this cluster will take place this Thursday afternoon, if I understand well. And I would like also to come to the EU mission, A Soil Day for Europe. Our unit is also responsible for this new instrument, and where we also have several projects addressing soil and crop monitoring. I think later on you will have some specific sessions on soil and crop monitoring, so I will be very short. The MARMIC projects aim at developing and testing a reliable framework for design of harmonized, context-specific monitoring, reporting, and verification system for assessing carbon stock changes in soils and woody biomass and soil greenhouse gas emissions. Artificial Intelligence for Soil Health project will develop and deploy the Earth observation-based soil health and degradation monitor by testing several technologies, including remote sensing for evaluating soil health indicators. So you see all the different cooperation that we already have and we already use in our research innovation project, soil observation. But to ensure that the sustainability of the solution, Horizon Europe projects are also assessing the impact of digital technologies in agriculture and assess the socioeconomic effects of digitalization in rural areas, a key component to be sure that what we support also reach our farmers and will be deployed later on. We also invest very much in sustainable digitalization of rural areas. We have also this territorial approach in DG Agri, as you know. We set up multi-sectoral digital services that supports the connection and sharing of data collected locally. And as has been said before, the capitalization of data is key for succeeding the digitalization. Under Horizon funding, the development of interoperability solution in agriculture, linking data from different sources and using them in different applications is supported. And I will be very short on the data partnership that Franz already mentioned. That is something that we do all together with DG RTD. The call has been opened some days ago, the 18th of April. And we hope that this co-funded partnership We'll develop innovative data solutions, and also we use the Earth observation as mentioned by Franz before. We are also working on the next work program, 2025, and we run stakeholder feedback. There was a stakeholder feedback opportunity that has been launched and just ended last week, where we hope that we will already get some very useful feedback, hopefully also from you, to be able to adjust our work program from 2025. So I wish you a very nice discussion, and I am very looking forward to the outcome of the workshop for our own work in DG Agri. Thanks very much.
Thank you very much, Ursula. And so then we go back live, because at the end it's a hybrid meeting, so we also have live performances. So we have the honor to have here the Director of Statistics Division from FAO, José Rosero Moncayo.
Thank you, Inge, and good afternoon to all of you. For the Food and Agriculture Organization of United Nations, it's a pleasure to be here today, having the opportunity to address you all in the inaugural session of this workshop that has a very provocative name or title, which is Earth Observation for Agriculture Under Pressure. As representative of the UN organization with a specific mandate in agriculture, it makes sense to make some remarks on the context that we have at hand. Dear friends, agriculture and more in general, agri-food systems are indeed under pressure. That's not a statement, okay? It is a reality. And the future of food and agriculture is full of uncertainties, uncertainties that impose serious questions and concerns regarding their performance and their sustainability. One element of pressure is, for sure, population, as today's agri-food system should be capable of meeting the needs of a growing population. The global population is expected to increase and reach 9.7 billion people by 2050. And this growth is not concentrated homogeneously around the world. It is concentrated in specific parts of the world, more specifically in Africa, South Asia, and the world cities. Associated with it is the pattern of urbanization. It is estimated by the year 2050, 2/3 of the world population will be living in cities, trends that will result in longer, more complex commercial food value chains to serve the new influx of people demanding it. Another element has to do with the change of dietary patterns, driven by the aforementioned pattern of urbanization and also by the rise of a middle-income class in low and lower middle-income countries as a result of accumulated economic growth observed in the last 4 decades, even accounting for the COVID effect. This transition translates to a demand for food that is changing towards higher consumption of a specific type of foods, like meat and dairy products, and food items such as fruits and vegetables, which are more resource intensive, with serious implications on the use of natural resources. So, higher population, more urban population with higher purchasing power and in dietary transition has induced an expansion of the demand for food. So far, the agri-food systems have been able to accommodate such demand, but this has come as a cost. One of them is the increase in agricultural land and deforestation observed in some parts of the world. In tropical and subtropical regions, agricultural area has expanded by 6 million hectares per year between the year 2000 and 2010, and annual forest losses amounted to 7 million hectares per year. Increased agricultural production has also led to water scarcity, where agriculture is competing for water supplies with the industry and the cities. And sustainable agricultural practices have resulted in 40% of the world rural population living in river basins that are classified as water scarce. Another of the costs of increased agricultural production to cope with higher demand for food is direct and indirect emissions of greenhouse gases. The agri-food systems contribute substantially to climate change, as they produce around 24% of the total GHG emissions and have nearly doubled in the last 50 years. But agriculture, my friends, is not only a contributor of climate change, it's also heavily affected by climate change. Climate change manifests itself in the form of extreme weather events, increased variability of precipitations, and higher frequency of droughts and floods. These type of events have a deep impact on yields in production, livestock activity, and aquatic production. A final element of pressure is the existing inequalities of access to food that configures this special situation in which, despite the existence of sufficient food in the world, at least until now, an important group of the global population is not able to consume the minimum dietary energy requirement to maintain a normal, active, and healthy lives. Around the world, 9.2% of the population, or around 750 million people, are undernourished, driven by situations such as structural poverty, economic slowdowns, conflict, and extreme weather variations. On top of that, in 2023, 705,000 people were facing situations of famine in countries such as South Sudan, Burkina Faso, Somalia, Mali, and Palestine more lately. In this context of agriculture under pressure, it is estimated that agriculture in 2050 will need to produce almost 50% more food, feed, and biofuel than it did in 2012 to cover the needs. Different regions will have to do even more efforts. It is estimated that in the sub-Saharan Africa and South Asia, agricultural output will need to more than double by 2050. And to do so, we need to transform our agri-food systems in a way that can feed the world, promoting healthy diets, and do so in a way that is sustainable and socially acceptable. That, my dear friends, is the challenge of our times. And this conference is situated in that context. And it is in that context that we value the opportunity to meet with the Earth observation community, to discuss the state of the art in Earth observation, in its application to food and agriculture, and the research challenges that exist to support effectively this agriculture under pressure and eradicate food insecurity. Now, Earth observation data plays a critical role in the Food and Agricultural Organization and its mission to achieve global food security and sustainable development. By utilizing satellite imagery and remote sensing technology, FAO can monitor agricultural landscapes and natural resources with precision and on a global scale. FAO is in fact using Earth observation data and geospatial technology to monitor land cover, crop distribution and productivity, crop health, soil conditions, and water availability. At the same time, it is allowing us to assess and monitor the impacts of climate change on ecosystems. Such detailed monitoring is essential for countries as it enables timely decision-making to improve crop yields, manage water resources efficiently, reduce the impact of natural disasters on food production, and promote resilience in the agri-food systems. At the same time, by monitoring production patterns, Earth observation data is helping us in enhancing food security and nutrition, identifying areas that are vulnerable to food insecurity, and assessing the availability of diverse food sources, facilitating targeted interventions. Moreover, Earth observation data assists FAO in addressing key agricultural pressures, such as climate change, deforestation, land degradation, and biodiversity loss. By tracking changes in land use and vegetation cover, FAO can guide policy and actions toward more sustainable farming practices and conservation efforts to mitigate climate change impacts and preserve ecosystems. Now, I cannot end these remarks without making reference to the critical importance of international collaboration on geospatial work. The vastity of the geospatial domain and its rapid evolution limit the capacity of one single organization to efficiently and extensively use them to address the complexity and multitude of challenges affecting agriculture and causing poverty and hunger. In such a context, FAO recognizes the strategic importance from partnerships, from partnering with the space agencies, international institutions, and other UN agencies working in geospatial, and to seek for synergies and joint collaboration, leveraging on each entity's respective strengths at the benefit of the overall quality, outreach, and impacts of FAO's work. In line with this philosophy, FAO has signed a Memorandum of Understanding with the European Space Agency in 2021, implementing a multi-year joint work plan. It is also an active member of GEOGLAM, supporting the development of validation standards and capacity building in countries in the use of Earth observation for crop mapping, and is also actively collaborating with WFP on several applications, including flood forecasting, as this has a direct impact on crop yields. We believe in partnerships and the power of bringing together the best of all of us to face the challenges that we currently face. Ladies and gentlemen, I look forward to the different discussions of this workshop. FAO is committing on leveraging Earth observation data for evidence-based decision-making, and we count on you in joining forces for addressing the multifaceted challenges facing agriculture and food security globally. Thanks very much.
Thank you very much, Mr. Moncayo. So now we go to the other sister agency, as mentioned by Mr. Moncayo. So we have the WFP, so the World Food Programme, also here in Rome. And we have Giancarlo Pini, who will talk about the Earth observation activities and needs.
Hello.
Hello.
Hello, everybody. Thanks for the invitation. I'm very happy to be here. I greet everybody. There is very high-level audience, and even if I am remote, I'm really honored to be with you today. I will just try to highlight which are our activities as WFP and which are our needs. For this, I have prepared a short presentation to highlight that will guide in the description. Just a second, I started. Okay, it's coming. So first of all, a short introduction on WFP. Most of you for sure knows, but it's always good. We are working in 100 plus countries, combining emergency assistance and long-term development to achieve zero hunger. Currently, the main drivers of crisis are conflict and climate shocks around the globe. As you know, WFP is an operational organization, so we must reply to some easy question that doesn't have usually an easy reply. So our country office, regional bureaus, our colleagues in the field, they always ask where is the crisis, why there is a crisis, when there is a crisis, who are the affected, how many they are. In our organization, there are different divisions dealing with different sectors. As Earth observation and climate, we try to leverage all this information available, try to inform WFP operation with a portfolio of products and service around the disaster risk management. So how we do that? We leverage, let's say, climate and Earth observation. We always work with the two kind of data sets together because one, most of the time, is show the effect of the others, and they are very strongly interlinked. It's very difficult to extrapolate. So we have different kind of resolution, as you know. We have global data set covering with a relatively near medium resolution, seasonal forecast, climate projection with low resolution. Then going to something more interesting also for the audience, probably high resolution like Sentinel-2 and Landsat that allow us to do some specific assessment on the hotspot area, but we cannot use at global level because it's still too heavy for our capacities. And so it's used exactly for monitoring specific hazards in some hotspot areas, and then very high resolution up to some centimeter to some very specific activities like camps, crop detection, earthquake. And We talk about the disaster cycle. So these are some of our products that we have on board, currently key products. They are a lot, but it's not enough. So, so you see from preparedness, response, recovery, mitigation, and resilience, we try to cover as much as possible all the needs that are coming from our colleagues in the field. And in the middle, we have our geospatial infrastructure recently moved to the cloud in order to be more efficient and also facing the incredible amount of data that is growing every day that we need to manage. And so one by one, very quickly, I want to show you the activity, these products and services. So we have in preparedness, the Adam Preparedness, that is a tool that analyzes the risk, spatial risk analysis, that is a basic for country office to plan the activities. Then we have a system that triggers the anticipatory actions. It's based on seasonal forecast that allows the triggering of activities that the country office can put in place when a drought, for instance, is coming. So start to have some action in the field before the drought really happens. This should save lives and money. Then the seasonal monitoring, that is the early warning tool that we use at global level, monitoring all the season around the globe with, maybe 15, 20 indicators, updated very quickly, each 10 days, 5 days. So this allows us to identify shocks, climate shocks, and impacts on crop production and pastoral production as well. Then the ADAM system for alerted tropical storms and floods, that is based on seasonal forecast, but and also some other meteorological information. Going now to the response, ADAM has also another component that relates to the hazard mapping, rapid hazard mapping, for instance, detection of flooded area, impact on population, impact on crop and pastoral surface. Then some specific hotspot analysis that like the South Sudan large floods, that is an example of using thermal data. Some models to detect, to understand the impact of a drought, providing population affected. Then, as you see, another example is the example in red here, where we detected cropland abandonment in some areas in northeast Nigeria. This is an example where we see that crop field has been completely abandoned, and this means, and for WFP, this is an important information, where these people is looking for food now, and where they are. And for the recovery side, we have some less activities, let's say for the moment, crop area and crop type detection, very critical information that we need to really strengthen and reinforce in our portfolio. AIMS detection is a system that allows the monitoring, the detection of some activities that WFP assets building in the field. So if an asset can be dams, can be irrigation schemes, land rehabilitation, this is the first step that allow even from remotely to detect if the asset has been realized, because some assets are realized in area very far, very difficult to reach, and sometimes very insecure. And the last one, for concerning mitigation and resilience, we do a lot with technical assistance to National Meteorological Service with a portfolio of products, providing them Earth observation climate data, supporting them in the analysis of this data set, providing them the tool for blending meteorological station data, and also an interface called Prism that allows them to explore and do some impact analysis. The second component of AIMS, our asset monitor system, that is the landscape impact assessment, meaning after the realization of an asset, we monitor for 3, 4, 5, 10 years, whatever, the impact, if the asset is working properly, it's working as we want it, as it's been designed. So in this, there are some cases like this one where we see that it allows to have 2 crop production in a year instead of 1. And then 2 basic products that are very important for the WFP 5 years planning. So these are really something that we need to provide to the country office to understand the climate, how the climate is going to change, how it's already changed. So we usually put together the historical analysis with the climate projection, and in most of cases we see that climate change is already here, it's already happened, so we don't need to wait until 2030 or 50. Okay, there is much, very fast. We have short time. I think it's just an overview of what we have, but it's not enough. And we think really that this kind of partnership, as was mentioned before, between the different organizations within the research community, with ESA, European Union, is extremely important. It's the only way to provide new information, useful information, and operational information for saving life and changing lives. So just a few examples here on how we can improve our collaboration. In the case of WFP, we would like to try to better do this step to uptake as a project outputs, like, and there's some example here where we are participating and making the transition from kind of research project to something that is fully operational and then be potentially transferred to local institutions, national institutions. Then innovation and research, there is a lot around this, and we should try to better engage with the field lab and to identify research topic or just to find some area of collaboration where we can really try to tackle some of the issues that we have in providing information to our clients in the field. So improve sharing of information between ESA and WFP and also other organizations in general. This is just ESA, but everywhere. And it's important to be informed what is going on around the globe and try to understand it and be in contact with the people that is developing something that could be interesting and integrated in our systems. And then I said before, computing resource and knowledge. There are still some limitations in using some specific data sets. Last slide, some really not exhaustive area of collaboration, crop type and crop mapping, very strategic for us. Crop yield production estimates, a dream for everybody. There is a lot of job, but it's something that we really need in the climate shock impacts, like now in the current drought crisis in Southern Africa. Then earth observation, crop phenology, flood water depth estimation. We know more or less the extent of floods, but we don't know how much the depth of these floods, and this completely different information that we should know. River discharge, water points monitoring, global level is particularly important for pastoralist community. This is a heritage of the long crisis, drought that affected the Horn of Africa a couple of years ago, and is expected to come back again with the La Nina in the near future. Land use change, the crop abandonment, that is extremely important to understand why these people is living and where now they are, and reliable earth observation derived products for agricultural and pastoral industry-based insurance. As you know, this is a tool that is going to be used a lot in the future, but it has a lot of limitation, mostly in the country where WFP is working. So reinforce the knowledge on the use of this product, provide effective information, and in general support the emergency and preparedness response. That is the core activity for WFP. But underlying everything is that being an operational organization, we need operational products that really provide the proper information, actionable information to the people that put in place the action. Thanks.
Thank you very much, Giancarlo. I think that's very good to know also because we're in the same Rome area, so we should strengthen our efforts. And then we go to GEOGLAM, which we have heard already quite mentioned, and we are very pleased to have the new program director, Sven Gilliams, who will talk about the essential agriculture variables.
Okay, thank you, Ian. Thank you for the introduction, and thanks for the opportunity to speak here. A warm welcome from GEOGLAM to all of you. I think it's exciting to see that the room is filling up. I think Espen mentioned that the goal was to gather the community. I think that's already a success with 300 subscriptions. We're very happy to be here with all co-hosting this workshop with the organizations with whom we work closely, but in the interest of time, I'm just going to dive into my presentation. So a bit of background on GEOGLAM. Some of you might have heard of us, maybe not everybody, but we started in 2011. We have a mandate from the G20, and actually the reason why we started was because of two major food price spikes, one in 2008, one in 2010, 2011. And so there was a reasoning that maybe that Earth observation could be an interesting tool to provide some transparent information and give us timely and actionable information on the agricultural situation. So that's how we started. We just got our mandate renewed in the G20 of last year, and well, we're working on the G20 that is happening, going to be in Brazil next year. Okay. So whenever I'm asked what is GEOGLAM and what do we do, I always show this slide and I spend the next 30 minutes on explaining it. I don't think that we have 30 minutes. I see Ingen already looking a bit nervous, so I'm going to go fast. So bottom right, you have policies. We have a lot of information products that try to provide an answer for those policies. Based on that, you get needs. And then on top of the slide, you have all the GEOGLAM working groups, where some of the GEOGLAM working group leads are in the house. And normally I would spend like all time on explaining all these different working groups. Basically is we have an R&D component, we have an operations component, and open source and open knowledge tools that produce that information products. We spend a lot of time on capacity and co-development, and so improve our information products. Although I said I'm not going to go into every work group, I especially want to mention one, because on Wednesday we have a very interesting panel on in situ data, and in situ was already one of the recommendations of the 2020 workshop. So the problem hasn't been solved yet. So I hope you're interested in that workshop, and my co-lead there, Rafael, I hope we can all see you on Wednesday for the discussion. So if I'm not going to explain GEOGLAM in the traditional way, how am I going to explain it? I'm going to link it to the EAV, our Essential Agricultural Variables. And so you can see GEOGLAM actually as a bridge between communities. It has been said before, like there's policy drives the needs. So we see ourselves between if you can say, the policy community and the data community. So policy is justifying and defining some of the needs. And then, of course, the data going up, you have the data value chain, where after analysis, you add continuously value, and hopefully you serve some kind of policy. It's not just data for the data or information for information. And to be able to do that in this complex environment, you need actually an integrator from EO data to impact. And that is actually what our essential agricultural variables are. It's that integrating. So it's satellite-based, and that's important for us. Satellite-based building blocks that, in combination with other non-EO information, provide or support actionable policy required information. We have in total 40 EAVs defined, and we have a 50-50 breakdown between climate and weather, and actually in the agricultural domain. The figure on the right is a work in progress. I think it's version 2500 something that Alyssa and I have been trying to map all the EAVs into one slide, and I think we're almost there, but probably the next discussion I have with Alyssa, we're going to change the whole thing again. Trying to make it a bit more concrete, in this slide I just tried to map EO application with some of the policy needs. So rangeland mapping, that is of course with livestock production potential, state and change of land and water in livestock. You have cropland mapping, where you need food production, crop type mapping, which is also related to food production, crop field boundaries delineation, crop condition, crop yield. So it's the typically things that we in the agricultural community do, but try to link them to a policy and a policy need and see what is needed and why it's needed and what is still missing. That's actually the whole idea behind the EAVs. I don't want you to read the whole list. It's just the example of the 40-ish EAVs. And what's important here is what we also try to do is link it with the ECVs, like essential agricultural variables is not a new thing. In other domains, they have been working on that, climate, for instance. So we try to link with those domains as well. And so where we saw that there was a link or that the definition in the essential climate variables was useful for the agricultural domain, we keep the same definitions. Central part is just a bit more complex explanation on that data value to policy level. So we've been working quite a lot on the ag domain EAVs, and it's a huge task, but we're not doing it alone. As everything in GEOGLAM, it's actually bottom up, so there's a lot of community projects and a lot of programs that are actually contributing to this. I put a few on the slide. So biggest one biggest one. The most known, I think, from GEOGLAM is the crop monitor, where we focus on crop condition. A project that was funded by ESA on world cereal crop type mapping for wheat and maize. In the new phase, they're working on other crops as well. So that's really crop type. There's a presentation on that also later this week. Asia rice, doing a lot of work on different variables for rice. Crop watch from China, crop condition mostly. And then you have the NASA acres, which is actually led by Alyssa, that actually was designed around the whole EAV concept and that we're trying to expand. And then, of course, they were mentioning in the opening as well, the Copernicus land services with a lot of the products that are really the basis for the information that is being used within GEOGLAM. So, it's not new work. It started some time ago. 2018 was the first meeting we had on that. 2019, we had a full workshop. Then COVID happened, so we had a lot of virtual sprints. And in 2020, we had the first version of the definitions of the EAVs published. Alyssa and I are the co-leads for that working group, and we have 27 stewards, some of them in the room here. So where are we at this moment? So like I said, the definition of the EAVs is complete. We had our first validation validation and documentation workshop that was on the mapping product, so on the mapping EAVs. We're working, or we're planning on the next one after discussion with Copernicus and the ET community. Evapotranspiration is high on the list for that workshop. We're doing the harmonization with other communities. I said like the ECVs we did, but there's also land use typology and border classes that we still need to do. Biggest work that is upcoming, and that's the ask of today as well, is we're doing a big gap analysis because there's still a lot of these products that should be available that are not available, which is limiting the impact of EO in agriculture. And we need to find out why, and that's the gap analysis. Is there still an EO data barrier? I think we're at the right place. We had the same discussion in Tokyo a couple of weeks ago with CIOS. Is there still EO data missing? Is in situ data missing? Is it just method? And that's why I think here the community is the right community, like on research. Is it compute? Is it other capacity? So those are the questions that we're going to ask or try to solve. And I'm looking forward to the discussions we're going to have and maybe solve some of these methodological issues, maybe in situ data and also the EO data. And with that, I would like to thank you and say I'm looking forward to discussions.
Thank you very much, Sven. And then we go to the last intervention of this session, but not least. So we're going to have a talk on machine learning and Earth observation for agriculture. So we have the professor of AI and data science from Wageningen, Mr. Ioannis Athanasiadis. I hope I pronounced it a bit correct. So unfortunately, we won't have time to discuss here, but the good thing is we can have a coffee discussion after this talk.
Thank you very much. Thank you for having me here. Welcome, everyone. Really happy to see you. I think if it wasn't for Eurovision last week, I think the major item on the news would be about AlphaFold 3. AI managed to solve the 50-year-old grand challenge in biology a couple of years ago with AlphaFold 2, and already since last week, AI is able to offer high accuracy modeling across biomolecular space within a single deep learning framework. That means that AI allows scientists to predict the structure and the interaction of life molecules all in silico. Is it something we could do also for agriculture? I think most of you, and I would agree with you, it's something that we have been doing already. We have a number of recent developments, but also older ones, that originate back to work of NASA about 25 years ago that has shown that with remote sensing images, we can identify when crops are under stress. We have facilities that monitor agriculture on a global level. And today, combined with data-driven AI, these kind of infrastructures are already getting in the hands of farmers. Also, another great success is the extensive application of machine vision for plant phenotyping. The community has advanced rapidly in the past decade since an open data set emerged, and the whole machine vision community started solving the problem of leaf counting and leaf detection. And today, we have high throughput phenotyping facilities like the one you can see here, at a large scale, all across Europe and in the US. Looking forwards, and this was a recent Nature food editorial, we have all components at hand. We have big data, we have computational power, and we do have a lot of experience. And this opens up opportunities for tackling food security problems at a different scale, more inclusively, but also more accurately. So it looks almost obvious that we have a lot of agri-environmental data, we have working AI methods, and we can apply them for addressing global challenges as food security, climate change, and biodiversity. Unfortunately, using AI methods from the shelf is not going to work. We deal with wicked problems with too many uncertainties where historical data are small and incomplete and also not representative of future conditions. Most of the current extraordinary results from a methods point of view boil down into pattern recognition, learning from feedback, learning from teacher feedback, so learning from data with labels. In a way, we have teachers that give out the answers to machine learning. So part of their success is also their weakness, that we need these labels. We need to collect labels in order to train machine learning solutions. And in agriculture, as was mentioned also before, these labels are very often missing. Therefore, we have a lot of solutions that are tailored to local conditions, but they cannot generalize well in space or in time. And this is a very big opportunity because it allows a lot of research to happen, but also gives a lot of opportunities to business and SMEs to develop and exploit these solutions in the local market. However, there is less focus in systems understanding, in how we can use machine learning and artificial intelligence for understanding agricultural systems. And this is something that I would like to talk about today, looking into three aspects. First, looking into data. Most machine learning developments are founded on open, large, standardized data sets. The recent AlphaFold 3 publication is supported only by open data. On the contrary, in agriculture, data sharing is limited and data sets are fragmented. In the AI community, data accumulate fast. In agriculture, not. One label per growing season is not really growing fast enough. But also, they are different in terms of tasks. In machine learning community, we're looking into standardized tasks, classification, segmentation, while in contrary, in agriculture, tasks are changing based on the availability of data on objectives. There is a lot of local effects, different kinds of questions. So this doesn't fit together very well. But also, there is a lot of domain knowledge necessary for selecting and preparing the data, as Sven just mentioned. We need a lot of knowledge, which are the right variables, how to set up the problem, while in the contrast, in the AI community, all this is fixed. Images are always RGB, text is text, and focus is on machine learning architectures. Also, there is a different focus in terms of the tasks. In the machine learning community, they focus on open benchmarks, looking into metrics, and try to optimize those. They don't care about the numbers and what they mean there. The prediction is the king. While in agriculture, focus is more on impact, on case studies, on collecting the ground truth and understanding the systems. So there is not a good match between the task definitions in the AI community and the task definitions in agriculture. And last but not least, there is a different community in terms of size, the way it works, and what is the mission there. So in the machine learning community, professional software libraries are there mostly for text and images, while in the agricultural community there is limited culture of sharing code. It's hard to reproduce results of others, and there is no culture for open reviews and benchmarking. In machine learning, we have a vibrant, growing community of sharing best practices, but this is not always how it feels in agricultural modeling. That's why I think that using AI methods off the shelf, it's not going to work for addressing grand challenges like food security problems. Therefore, we need a different approach. And that approach requires a hybrid artificial intelligence approach that is tailor-made and uses the prior knowledge of agricultural systems, but also focuses very much on benchmarking. And I will show you a couple of examples on how we have been doing that with my team in Wageningen, but also with a global community of AgMIP. So first, how to include domain knowledge. Let's see what we can do where we have better organized and relatively complete data sets, using as an example the case of regional yield forecasting in Europe. The system that it has been in place for decades now from the European Commission is by the Joint Research Center, provides national crop yield forecast at the national level using statistical models, a variety of data, and expert information. So while successful, it has been little improvement in the quality of the forecast in the past decades. And this is where we investigated how machine learning can come into help. So we developed an end-to-end machine learning pipeline that included designing features from the same data, but with expert knowledge into which variables need to be included and which not, and develop machine learning to predict yields both at the national and the sub-national level. And we did a thorough evaluation with 35 case studies in 9 countries and 6 crops, producing both national and sub-national forecasts. And this improved predictions in 25 out of 35 cases and regional forecast like these ones offers new insights addressing the spatial variability in food security issues. But also, this helped us to better understand the uncertainties involved in the European food production systems. To further demonstrate such an approach, we also applied it in the US, following exactly the same pipeline, and it was tested both at a county and 10-kilometer grid, showing similarly good results. With this example, we can see how data-driven AI may help us address issues related to food security at scale, but also how we can all benefit from standardizing data and comparing methods before a single case study. And this is the value of benchmarking, which is also very important. Such forecasting systems still struggle with making reliable predictions in a changing climate, and especially because we don't have ground truth data. Driven from the need that there is no high-resolution labels, we also developed an architecture where we employed weak learning, so learning from low-resolution labels using high-resolution inputs in order to produce high-resolution yield forecasts. And in this case, we put together remote sensing products with weather and other variables at high resolution in the US and in Europe, and we were able to produce, without using high resolution labels, forecasts at a high resolution. This approach, called a weakly supervised approach, can help us address some of the issues inspired from the problems of the agricultural domain, because we are not going to have high resolution yield labels anytime soon. Our results proved to be statistically equivalent with those produced with strongly supervised approaches. Last but not least, I would like to bring our attention also into benchmarking, and I will introduce an initiative that we started a couple of years ago within the AgMI framework called AgML, for machine learning for agricultural modeling. We started some discussions at the end of 2022, and we launched it as an activity last summer, and we have a very vibrant, interested community. It's open to everyone. You're very welcome to join us. A mailing list with more than 250 members and bi-weekly meetings with more than 30 to 50 participants every 2 weeks. And what we are doing is what we want is to establish an interdisciplinary community to facilitate knowledge exchange and collaboration, to coordinate activities at the global level on how to facilitate research progress on the interface between machine learning and agricultural modeling, and most importantly, to create benchmarking protocols to learn about the strengths and the weaknesses of the various approaches. So far, we have organized AgML in 2 activities. The first one is on future climate impacts on yields, and we are, the goal there is to measure the skill of machine learning models to emulate future climate change scenarios, while the second one is focused exactly on what I showed before, on subnational yield forecasting, but now we want to intercompare at an international level across different systems in Europe, in the US, in sub-Saharan Africa, in East Asia, and to try to answer questions like, do machine learning models perform equally well in different regions and for different crops? And to do that, we organize our work in a benchmarking protocol where we bring together data, research questions, and define experimental setups and tasks, multidisciplinary metrics, and hopefully we will have some papers at the end. Both tasks are in heavy development these days, and we follow a different approach. The first one is with emulated open data, which is more straightforward in terms of licensing and what is available, while in the second case of subnational yield forecasting, data are open, but they are vary a lot in coverage, in how they are shared, in licensing, and how they are becoming available and when. So this is more or less the status of where we stand today towards creating this benchmark. We're working with 2 crops, maize and wheat, and we have 3 tasks inspired from an operational use case for having end-of-year yield forecasting at mid-season, between mid and late, and 2 weeks before harvesting. And we want to develop this, and we are looking for contributors to help us develop this dataset all across the world. So our AgML perspective is to establish the domain-specific performance of current machine learning methods and models by defining evaluation criteria that reflect multiple stakeholders to develop trustworthy benchmark datasets to drive machine learning research progress and reliable estimates of machine learning utility for different applications through intercomparison studies. So by using several architectures, comparing how they perform in different countries for different crops and in different conditions. And this will allow us to improve our understanding of the strengths and the weaknesses of state-of-the-art machine learning methods. So if you want to join our activities, please join our mailing list at agml.org. And I would like to summarize my talk today by 3 suggestions, as it was instructed by the organizers for today. So the first one is that public truth, ground truth data is a public good. And this is necessary to evaluate models and accelerate impact. And while Earth observation and meteorological data do have clear custodians and networks, that's not the case for agricultural data. There is no agricultural meteorological service or ESA or NASA equivalent. So that's why we're always talking about where the ground truth data are coming from, and we have different protocols, different institutions in every country that makes the thing very, very difficult. The second message for our discussions this week that I would like to bring up is the value of benchmarking. So we need to define clear benchmarking tasks to be able to reproduce results of others and accelerate progress. Our research is mostly case study driven, and how we organize tasks in terms of definitions of what we want to predict and what are predictors, or how we define the protocols for evaluating our results, depends from study to study. That's very, very difficult if we want to intercompare. Then we don't know why something works in a location and not in another location. Does a solution we have done for Europe and the Mars system will work also in Africa or in Japan? We have no idea. And last but not least, I would like to bring the point of thinking of the stakeholders and the added value first. Bring agriculture first. Don't look at Earth observation and don't look at machine learning and artificial intelligence as a golden hammer that can solve all our problems. We need to be really critical in for what reasons we're using AI, and if it indeed brings an added value to our products and our services. And I think as a scientist, we need to be fine if this is not the case. But we need to have protocols and benchmarks to be able to measure it. And with this, I would like to thank you very much and wish you great success for the whole week. Thank you.
Thank you very much, Yanis, for this inspiring talk. So as we heard from the organizers, we're here together, which we do, and also to see for the current needs and to see what the future will bring. So the near future brings coffee, and the coffee is just here in the tent. And I would like you all to come back 3:30 for another very interesting session. Thank you so much.
Hello, good afternoon. Should we perhaps slowly start again the next session? I think somebody should tell the rest of the people outside in the coffee break that it's time to get serious again. Let's hope my... Okay, so let us start the next session. Which will be on new missions in the agriculture science domain. We don't want to introduce you to all the existing missions already because we know that you use them. That's the reason why you're here, I suppose. So we have in this session really two different components. One is more the institutional missions, which we propose for the future, the Sentinel next generation and expansion missions, and one Earth Explorer. And then it will be complemented by some new space missions and also science missions from NASA, which will give us basically the future, what type of measurements we will have in the agriculture monitoring and scientific community. My name is Benjamin Kurtz. I'm here working in ESRAN. I'm the mission scientist for LSTM, besides some other activities. But let me introduce you, Michel.
Yeah, good afternoon. I hope it's working. My name is Michel Massard, working for the European Commission and working on Copernicus. And I will have the pleasure to chair this session with Benjamin today. I think we have to go quickly. If everybody is back, we have to go quickly because the time is short. And we will start with a presentation on S2 next generation of Sentinel 2, which should be launched after 2030 and will ensure the continuity with the current Sentinel 2. And then Marco Celesti will present this mission. Also, he will present the CHIME mission, which is an expansion mission in the context of Copernicus. Marco, if you're online.
Everyone, I hope
yes,
you can
perfect.
hear me well. I'll share my screen then.
Marco, you have 7 minutes to be precise.
Yes, can you confirm? Can you please confirm you see it in presentation mode?
Yes. Yes.
Okay, then I will start. Thank you. Yes. So thank you for the introduction, Michel and Ben. I'm going to present, let's say, in chronological order of expected launch, CHIME first, and then brief introduction to Sentinel-2 Next Generation 2. Starting with CHIME, indeed. CHIME is an operational hyperspectral mission which is optimized for terrestrial ecosystem monitoring and supporting related policies, applications, and operational services. In order to do that, the key specifications of CHIME observations are that is based on a carpet mapping observation patterns of all emerged land and of all coastal areas. We are limited in terms of sun zenith angle above 84 degrees, but apart from that, we will observe routinely over the year over basically all major islands and all the spectral range that the CHIME will cover is between 400 and 2500 nanometers. And this is done by means of a constant spectral sampling of about 8.4 nanometers between neighboring bands, with a full width of maximum of about 10 nanometers. The ground spatial resolution will be 30 meters, and the swath of a single CHIME acquisition will be about 130 kilometers. 2 satellites in orbit, which is the final configuration of the constellation, we will reach a geometric revisit of 11 days. All this by ensuring a high radiometric accuracy and high SNR, low spectral and spatial misregistration across all data products, which in terms of operational data products are top of atmosphere radiance in sensor geometry, orthorectified top of atmosphere reflectance, a la Sentinel-2 level 1C, and bottom of atmosphere land surface and aquatic reflectance, which we are going to produce at least, which we'll be able to produce in sensor and orthorectified geometry. In terms of the space segment, the prime who's building CHIME is Thales Alenia Space, with OHB leading for the instrument. We are in phase C. The CDR is expected Q1 25, and the first CHIME unit will be ready for launch from the third quarter of 2028. This is more or less the time frame. In terms of what we are preparing for the exploitation of CHIME, level 1, level 2 products, we are prototyping some of what we consider the key higher level products related to the CHIME primary applications, which is supporting basically vegetation and soil monitoring for agriculture, as well as geology and mineral mapping. But when it comes to agriculture related products, we're prototyping the retrieval of leaf and canopy nitrogen content, leaf and canopy water content, and leaf mass per area. When it comes to soil, we are prototyping the retrieval of soil organic carbon. This, of course, with the aim of preparing the ground for further products down the line, like nitrogen use efficiency or carbon stock monitor, carbon stock account. Just very briefly on Sentinel-2 Next Generation, as Michel said, this is in view of enhanced continuity of Sentinel-2-like observations for Copernicus. So this will combine, as it is currently for Sentinel-2, very high image quality, high spatial resolution, but also high frequency of observations, and a sampling of important spectral features in the visible, near-infrared, and shortwave infrared. So the same spectral range covered by CHIME, but instead of having, let's say, continuous sampling in this hyperspectral fashion, we will have still a multispectral approach like Sentinel-2. This is coupled with low latency for level 1 and level 2 products, again, produced routinely and distributed through the Copernicus Ground data ground ecosystem. And then these 3 dots are for the many more features that we're all used to for Sentinel-2 and that we will work to preserve also in Sentinel-2. A full list was definitely not possible in these few minutes. Now, in terms of visualizing the most critical enhancement, here is a plot of the current Sentinel-2 spectral bands. Here the spectral wavelengths. Here the spatial sampling distance in meters, and here just the when we move from Sentinel-2 to Sentinel-2 next generation, basically we are improving the spatial resolution for all bands but the atmospheric ones. We're moving to 5 meters for the RGB near bands and to 10 meters for basically all other bands oriented at dedicated, to monitoring of terrestrial systems. Then we have a number of bands are at 20 meters. Actually, I apologize because this plot is slightly outdated. We are currently baselining to have the split B12 ABC into 10 meters native spatial resolution. So please consider these 3 spectral bands in the 10 meters SSD level. And I think that in terms of, let's say, the other main element where we are working on is increasing the temporal frequency of observations. We are aiming for 3 days over Europe, pending the availability of 3 satellite constellations for Sentinel-2 next generation. And with this, I thank you very much for your attention.
Thank you, Marco. We decided, in fact, to present you 3 of the 6 expansion missions of Copernicus, which will be launched in between 2025 and 2030. So now we will move to the second one, which is Rose-L. Malcolm, if you are ready, the floor is yours.
I'm ready. Can you hear me?
Yeah.
Okay.
And then
good. So.
Yeah. Okay, you will present also Sentinel-1, next generation. Yes. Yeah.
Correct. So I will try and present many person years of work in 7 minutes, which will be a challenge, but let me give it a try. My pleasure today to bring to your attention the Rose-L and Sentinel-1 next generation missions, and I do so on behalf of a large team of people at ESA and with industry working on this mission. Now, there's a few basic elements that I would like to get across. The first is the timeline. You see that we are currently in the era of Sentinel-1 first generation, which we sometimes refer to as FG. And in the near future, there will be the launch of Sentinel-1C and Sentinel-1D, which will assure continuity in the sort of immediate time, the 2032 timeframe, which assures enhanced continuity of the Sentinel-1 first generation. Rose-L has been designed, first of all, to work in combination with Sentinel-1 first generation. It has the same orbit, and it has the same swath width an even higher resolution than Sentinel-1 does. So we expect Sentinel-1 first generation and Roselle to work as a system of systems. And similarly, we're also in the process of designing Sentinel-1 next generation to fulfill that very same function, which means that Sentinel-1 next generation will also have the same orbit as Sentinel-1 first generation and Roselle, and it will have enhanced capabilities in terms of resolution. We expect a 5 by 5 meter resolution, which is good in order to be able to resolve smaller fields, for instance, within Europe, and a larger swath, with the exact width of the swath to be determined, but somewhere between 300 and 400 kilometers, which will also provide enhanced coverage of Europe and the world. So the paradigm is very much that of enhanced continuity, building on Sentinel-1 first generation, Roselle coming along in the 2028, 2029 timeframe, and Sentinel-1 next generation. So that's the number one message I want to get across. These missions are coming and will be there to be used for agricultural purposes at European and global scale. The next is to outline that these SAR missions are multi-purpose. They have a number of different applications, of which I would draw your attention to land use, agriculture, and forestry. That is one of the 6 big applications that these missions support. But there are other ones, as you can see. There's soil moisture, geohazards, cryosphere in the Arctic, marine monitoring, and also monitoring icebergs and vessels and these elements. And here you see the mapping into the various Copernicus services. I have 1 or 2 slides that provide more information on land use, agriculture, and forestry, but I did want to give you a feeling that it is a multi-purpose mission. To me, this is the key slide that I want to communicate to you. It's the information that we expect these SAR missions to provide for agriculture and agriculture applications. First point is that SAR missions are playing an expanding role in agricultural monitoring. Recall that agriculture monitoring in the past has been mostly, and still is mostly, based on optical or perhaps thermal infrared sources, but there has been an increasing uptake with the help of Sentinel-1 of the use in agriculture for SAR missions. I'll draw your attention to a few examples that I know of. One is the monitoring of rice crops, area growth stage, a number of planting cycles. This is, generally speaking, near operational and running quite well in areas such as the Mekong Delta. And another example that I'm keenly aware of are the yearly crop maps generated for the entire UK with SAR. One of the characteristics of SAR is that it sees through clouds and thus carries its own source of illumination. So one of the key elements for agriculture is that there are guaranteed acquisitions and regular time series through night and day all-weather acquisitions, so that there would be an increased revisit through combined Roselle and Sentinel-1N next generation to capture rapid changes in crops, even in conditions which are difficult for optical systems to take images in. The information that comes from these missions is complementary to optical and thermal infrared systems. Radar is mostly sensitive to crop type and crop status, but it is so in a completely different way because it is generally looking at structure rather than color or temperature in terms of getting its information. And the other element I would underline is that in addition to providing information about the agricultural crops and crop status, areas and so on, SAR does provide additional complementary information that can help. Soil moisture, soil roughness, for instance, which serves as a proxy for agricultural management practices, and sub-canopy flooding or the presence of water, and that's indeed what is used quite often for rice monitoring. We have a few examples here. One is an example simulated Sentinel-1 next generation image of field areas in North Germany. You also have here the combined revisit of Sentinel-1 next generation and Roselle, which indicates that you're very close to a one-day coverage of Europe using either one of two Sentinel-1 next generations or one of two Roselles. And here are some examples, sort of pre-operational products at 1 kilometer of soil moisture, just to underline the complementarity of the information that also has a big agricultural potential. Here's another example of the types of information that Sentinel-1 and L-band provides. Overall, it's simply indicating that there will be enhanced land use, land cover mapping, and crop monitoring by using both wavelengths, so by using Sentinel-1 next generation and Roselle together. And I finish with a slide, which is conclusions. So Sentinel-1 first generation has played a big role developing new operational applications, including for agricultural land use, land cover areas. Next generation is going to be there. So number one message is that there will be continuity of services, continuity of data, will be enhanced in terms of resolution and in terms of coverage. We expect it to enable new application development, as well as serve the already established applications. And the Roselle at L-band will address some of the information gaps that are there at C-band and will provide complementary information and coverage. We expect all of these elements together to act as a system of systems and support users and applications in the agriculture area at European level and worldwide. And with that, I close my presentation.
Okay, thank you, Malcolm. Now thermal infrared sensor was missing on Sentinel-2, so for the expansion mission, we have decided to improve the situation and optimize this situation, and that's why we have the LSTM mission, which is the third expansion mission that we will present, and Benjamin will tell you about it.
Yeah, thank you. So indeed, the LSTM mission really wants to fill in the observational gap for agriculture monitoring in terms of thermal observations. It's adequate spatial resolution, so field scale type of resolution in Europe and at global scale. So you see this is really driven by a large number of people. Some of them are sitting here in the room, including my colleagues from ESTEC, but also the scientists who are running the mission advisory group. Before I start talking about the what of the mission, I would like to say why we're going to do that. I mean, it's an observational gap which was identified by the European Commission in the Copernicus framework, because we have this need of understanding how agriculture under pressure is actually reacting. And you see here from the IPCC assessment report that at least for Europe, we have losses in crop productions and water scarcities foreseen as one of the key risks identified. And that is certainly something which we're already starting to see, and we need to react on it. And I'm talking here about Europe in the moment, but for sure that is even at a more alert stage in the global scale. And I hear from our colleagues in Asia, Southeast Asia, that they are fighting actually with temperatures which they have not really dealt with these weeks before. So I think we're already not looking at the future, we're looking something which is happening now. So that's why the LSTM mission objective is really looking at agriculture or sustainable agriculture management services to use thermal observations to increase the more crop for the drop. And I cite here our colleagues from FAO, who is using that very well to highlight what water productivity is all about. It brings it down really to the point, and that's what we want to contribute to it. Obviously, we don't save everything from space, but I think it's a very essential missing observational measurement which we want to contribute to from space. So that is really the key features of the mission, and you see here all the different, let's say, specifications of the mission. You see it's going to be 2 satellites. With that, we're going to get a 2-day revisit at equator, and that's perhaps not good enough, but it's increasing a lot the frequency, and it's in theory is getting to the point that we can follow it weekly or even even lower resolution in terms of temporal the needs of the understanding of evapotranspiration, and with that the needs of irrigation of the single farmers. We're using here the resolution of 50 meters, and we're really talking about 50 meters across the swath. That means at nadir we have a 37 meter resolution, which is quite a feast to actually achieve that in the technical terms for 11 spectral bands. And you see here also the rest of the specifications, which are basically outlining the performance of the instruments. And we do focus for this year actually to achieve the CDR, the critical design review, where there is a lot of things to be done in the moment from industry with my colleagues from ESTEC, and to understand if we can actually fulfill all these criteria, because it's quite challenging to achieve it. But we do want to have evapotranspiration at the daily level with the accuracy of 15%. So what we're going to deliver is these products. You see there's level 1 and level 2A products to be delivered. First, on level 1, you will have radiometrically and geometrically calibrated top of radiance information in the vis near range. These are bands which are in line with the Sentinel 2 bands, so they really make also here a system of different missions and synergy. And then it's being complemented by 5 thermal bands in the range of 8.6 to 12 micron, which will allow us to retrieve land surface temperature and land surface emissivity. So we have a kind of a consistent observational set to arrive something which can directly feed into models to derive evapotranspiration. All that with a very demanding data latencies, because we would like to actually deliver this information the next day to the farmers so they can react on that and make a decision on their irrigation, and with that substantially hopefully reduce the water resources needed to produce the crop for the drop. So I'm coming here to my last slide, because we do work with a number of different missions around the world. Here I mentioned here Trishna and SBG, both of them either owned and built by CNES and ISRO together for Trishna, and SBG built by NASA and ASI. Together we really work together to make sure that they have the same orbit, the same local overflight time, and making sure that there's also a minimum of data formats coordination, so we can use these data sets together to really get a daily revisit, and with that hopefully to really capture the agriculture dynamics over time in space. That's what we're trying to achieve, and I'm looking forward also to the presentations from the, let's say, more new space companies, which will come up after this presentation, and that hopefully will then complement also this type of measurements. That's for me. Michel?
Perfect. Thank you. You have been perfectly on time, so the last presentation of this mission is on the FLEX, which is not a mission of Copernicus, but it's a Nisar mission with member states. But it's, of course, complementing very well what Copernicus is doing also, and the missions of Copernicus. Jose.
Okay, thank you. As indicated, this is not the Sentinel kind of mission. It's more a scientific mission within the Earth Explorer program. And actually, the FLEX mission was selected by ESA as the 8th Earth Explorer in 2015, and will be launched in 2026. And the main objective of the mission is the quantitative global mapping of the actual photosynthetic activity of terrestrial vegetation, accounting for the variability which is driven by the environmental conditions. Primarily, the objective is the better knowledge of the role of vegetation in the global carbon cycle and improving the carbon fluxes, in particular gross primary productivity. But there is also a secondary objective, which is to provide the indicators of stress in vegetation, which are also useful for applications as agricultural food security. The key measurement is the vegetation fluorescence, the chlorophyll fluorescence emission, which is perhaps the best proxy we can have to actual photosynthetic activity of vegetation and also stress indicators from space observations. The instrument itself consists of two spectrometers, one with a narrow spectral coverage, but a very high spectral sampling of 0.1 nanometers, and another spectrometer with a wider spectral coverage, but with lower spectral sampling, and the combination of two is what provides all the information we need. But in order to get the objectives we have, and this information will not be enough, this is why we are flying in tandem with Sentinel-3, so that the combination of instruments on FLEX and the instruments on Sentinel-3 will provide the information from the blue up to the thermal infrared, which is all we need to provide the information we are looking for. Now, why this mission is relevant for agriculture, basically what we have been using so far is surface spectral reflectance and the changes in spectral reflectance as indicator of the vegetation status in agriculture. By the same way, we can use the fluorescence spectral emission, as illustrated in the figure on the left, which is another kind of indicator that will tell us additional information about vegetation status. Briefly, we can say that reflectance gives us the amount of light that has been absorbed by vegetation, and fluorescence will tell us how vegetation have used the absorbed light. Actually, in order to be a little more quantitative, we can think of the problem as when the light is absorbed by chlorophyll molecules, then the electrons are moved to an excited state, and they can go back to the ground state by basically 4 different mechanisms. One is the photochemistry, which is the photosynthesis at the end, but there is also energy dissipation through heat, regulated and basal heat dissipation, and there is also fluorescence. And fluorescence is a kind of residual of the light that has not been used by plants for photosynthesis. So basically, what we measure in FLEX is, on the one hand, how plants absorb light, separating the contribution from chlorophyll from other pigments, which are not photosynthetic active. Then we measure the amplitude and shape of fluorescence emission. And then we also measure how plants regulate the energy dissipation through these mechanisms, which are illustrated in the variability in surface spectral reflectance between 500 and 600 nanometers, which is related to the lutein and xanthophyll cycles and other photoprotection mechanisms. So by measuring all these components is how we can get the actual photosynthesis, which is useful for agriculture, because then this is a very direct indicator of plant status and functioning. Perhaps the most relevant aspect or the unique role of FLEX products for vegetation stress is this unique capability that at the end of the story, all the different stressors that can affect the vegetation somehow translate in changes or adaptations in the photosynthetic strain. So basically, fluorescence is a kind of reporter or how the different stressors that may affect vegetation will at the end change the photosynthetic rate. And all these stressors are somehow going together by coupling the carbon and water cycle. So basically, if plants will not be subject to stress conditions, the relationship between photosynthesis and fluorescence will be a linear relationship, but a negative correlation. So, because basically both will be competing by the absorbed light. But as soon as stress develops in plants, then there is other mechanisms which are in place, which are the photoprotection mechanisms, and then the relationship turns out to be to change in a nonlinear way, getting a positive correlation between fluorescence and photosynthesis. Until all these photoprotection mechanisms are not longer efficient, then we just write to the photoinhibition, and then again, there is a negative correlation between fluorescence and photosynthesis. So basically, by tracking all these relationships between fluorescence and photosynthesis, we can see how plants are affected by the stress. Another way of looking at this is the fact that any stress induced in the plants somehow will change the capability of the two photosystems, PS1 and PS2, to work in optimal conditions. So basically, stress will induce an imbalance in the capability of the two photosystems to move the electron through the photosynthetic chain. And this is reflected also in the shape of the fluorescence emission. So by looking at the changes in the shape of the fluorescence emission, we can monitor how PS1 and PS2 are being affected by stress conditions. So all these capabilities are already well known in the vegetation community by field experiments and laboratory conditions. The new thing in FLES is that we will be able to do that at the regional and even at the global scale when the satellite will be launched in 2026. Thank you. That's all from my side.
Okay, then we have now, thank you very much, Jose, for this scientific outlook for FLEX that's pushing the borders of measurements. So we now go to a presentation on the Constel IR constellation on the thermal infrared observations presented by Daniel Spengler. And while he's walking up, I would like to highlight we don't have time foreseen for discussions and questions for each presentation, but in the end of this session, we would like to give you the possibility to ask questions and also to give recommendations how we could perhaps use most these missions, perhaps even in combination with missions like Constel IR.
Thank you, Benjamin. So my name is Mathieu Teymans. I'm replacing my colleague Daniel Spengler for this presentation, and really happy to speak in front of such a beautiful audience this afternoon. So at Constellar, we are building a constellation of satellites for land surface temperature monitoring to support food security. We know that a small shift in temperature can make a big difference and creates a lot of new challenges around the world. And when there's new challenges, we require new data. And that's why we have set ourselves the mission to support agriculture by accurately measuring the land surface temperature of the field at an unprecedented resolution. We know that temperature is very dynamic and crop evolve quickly, so we also focus on high revisit time, and we also appreciate that the management scale for the field is the level of information that is needed for the farmer to get the information at. So we provide information that are timely and that are accurate at a scale that are adapted to the farming operation. We also position ourselves as a precursor to the other missions that were just presented, and we want to work jointly also with the institutional mission to be a complementary mission to the great work that is being done there. And so we have just heard about SBG, LSTM and Trishna, and we position ourselves there with some limitations due to the fact that we are a tasking mission, but with an opportunity also to work together to tackle the challenges that are occurring today. So our mission is called High Precision Versatile Ecosphere Monitoring Mission, HIVE, and it's a constellation of thermal satellites, as I have already mentioned. Firstly composed by 5 satellites, which both hold 2 different payloads, one visible and near-infrared payload with 10 bands, ranging from 440 nanometers to 940 nanometers that are aligned to Sentinel-2, and 4 bands in the long-wave infrared, ranging from 8.6 to 11.75 micrometers. We see also that there is synergies in these bands with the other missions that I have mentioned to provide this complementarity. Our technology is based on a cryo-cooled sensor with a swath of 20 kilometers, and we will reach a resolution of 30 meters at nadir. We also emphasize the importance of reaching a high accuracy, and we are working closely with LSTM and Trishna also on ensuring this high accuracy of less than 2 degrees Kelvin. Our next milestone is our first launch, which will occur in October 2024, and we have made great progress in that regard with very good performances that have been displayed in the testing, on the ground testing for the payloads. And we have recently mated the payload with the platform, so the satellite is now one piece, one together, and we are initiating the testing with the support of our partner and of ESA. We have also been selected as a data provider as part of the Copernicus contributing missions, category 1. So we will be providing our datasets to the services, and we are already undertaking some proof of concept studies with our dataset with some of the services. In terms of products, we plan to display this product portfolio in 2025, so after the first launch of our satellites. Starting with the central product that you see here, the Constellar High Precision, which is the level 2 data of our satellites, and expanding it with one super resolution product based on that product, and one other product which is called Constellar LST, which is based on the harmonization of existing land surface temperature dataset with our own data to ensure better coverage and to have like a baseline mapping of the temperature. Along with that, we accompany our customer and our partners with some insights provision that we provide in the format of a kind of a support or a consulting product, which is our Constellar Insight product. Some experiments that we have already done with some customers shows, for example, here some temperature anomalies related to irrigation failure and stress at the parcel level. Here we see maize crop in the US over a season, and we see that during the season some part of the field are being more stressed when we look at the level of anomalies on the LST coming from the harmonization product that we are already generating today. Another example of how we use this land surface temperature on agriculture is the optimization of seeding depth for corn to improve crop uniformity. We know that corn is very much subject to inter-plant competition, and this leads to an important impact on the yield. And so we want to ensure that at the field level, the crop is growing at the same stage homogeneously. And we do that by providing the initial condition for seedings that can inform our customer on the depths at which the corn needs to be seeded to improve the homogeneity at the field level. So that's two examples on how our data are being used for agriculture purposes. Our whole mission is really tailored for agricultures, and all the specifications have been also geared towards supporting food security. And the next steps are for us, as I mentioned, the first launch of our first satellites in October, and then 4 upcoming launch in the next 2 years, and then the scaling up of the constellation in the years to come. That's it for me. Thank you very much for your attention, and let's be in touch to co-create nice projects and products.
Thank you, Daniel. We will take the questions after, if there are questions here. Okay, so we'll take the questions.
Okay, yeah.
So thank you for this presentation and this promising development, which will complement, we hope, LSTM and offer more possibilities for these thermal mission observations. Next presentation, we're moving from the private sector to member states missions, and with the development on Prisma and MAP. And so, yeah, these missions have been a really precursor for SHIME, and that's we are very happy with that, and we follow the development of this mission and the research, the application that you are developing, because it will be a very good start for SHIME mission and the application that we will develop in SHIME. And so, Mirko, you have the floor for the presentation. Thanks.
Okay, good afternoon, everybody. I'm honored to speak here. I'm Mirko Boschetti from the National Resource Center, the Institute of Electromagnetic Sensing of Environment. My institute is more famous for that kind of things there with the SAR data, but we work also on agricultural monitoring. And I'm presenting a work done together with Gabriele Candiani and Monica Pepe, that she's in the audience, so if we wanted to later on speak about this stuff, we can do it later on. Okay, as I was introduced, okay, what we are working is on Prisma data. The framework is not why it's important to monitor remote to monitor agriculture with remote sensing, but with new satellite sensor. So we are expecting an unprecedented flow of data from space-borne spectroscopy. And one of the precursors, as was mentioned before, are of course the mission from Prisma IASI and map of DLR. They opening really a new era because we have data available on that we can analyze to produce retrieval methods. Of course, there are other missions that are ongoing, but we are all waiting what Marco Celeste was mentioning before, that is the arrival of the CHIME as European, but together with also the American mission of SBG from Nisar. So the reason why CHIME is that it was support and pushed. You mentioned this morning that the Copernicus mission are user-driven to contribute to food security and agricultural monitoring. So there is a big expectation of this kind of data. And why that? Because we know that space-borne image spectroscopy can help in efficient monitoring of crop traits during the season, so providing information for decision maker, precision farming and yield prediction, and at the end of the season to quantify the NPV, non-photosynthetic vegetation, and in particular the crop residue that remain in the field. And this is extremely important for soil conservation practice and carbon farming. So there is a need to develop a methodological solution as in preparation of the CHIME SBG mission. So here you can see a typical Sentinel-2 spectra for a wheat field from the sowing, when you have bare soil, up to the harvesting, when you have just the crop residue, and in the middle, the development of the crop, in the tillering, stem elongation, flowering, till the maturity. And this is the contribution that we can expect, that actually we have from Nmap and Prisma data in terms of hyperspectral information. We can add much more information. And what we can see in particular is to have a spectral continuity in the near SWIR region that allow us to characterize spectral absorption features that are extremely important to retrieve information, particularly for protein, lignin, and cellulose, as Marco Celesti was mentioning before. And this can be done only with a complete spectral range at a continuous bands. So what we do is to develop a retrieval algorithm for these two big categories: green vegetation during the season, so crop traits, those helps in providing information on crop nutritional status and crop stressor, and at the end of the day to help in yield forecasting. And at the end of the season on non-photosynthetic vegetation means crop residue mainly for information indicator for crop practice and carbon farming. Data, we were mentioning the importance of data this morning from Ioanni's speech. So we are working in this area since several years. It is the biggest Italian farm, is more or less 4,000 hectares. And we conducted several projects. It's an ASI project, and is actually a test site for the pre-SCAV activity and for the HyperNet activity that are all devoted to calibrate and validate hyperspectral satellite data. And is ongoing, the project are PRIS4VEG, that is the HASI project in which this activity was framed. And another important is a project that is the EO for Nutri. So since 2020, we acquire regularly, according to the characteristic of the sensor, hyperspectral data together with ground information, crop parameters. So again, I mentioned what Ioannis said today, that we need this kind of data, ground plus remote sensing to perform algorithm validation and calibration. So for what regard green vegetation, the framework, the methodological framework is framing what is called the hybrid approach, means that we try to use radial transfer simulation plus machine learning algorithm to develop what are the training the algorithm and having the solution, but we saw that when we had real data, so again, the importance of data, that comes from the Prisma in this case, plus the field activity we conduct, the results are much more better. Then we do an independent validation to see how strong are those modeling with the multi-crop, multi-seasonal data that I showed you before. Here are the results. For the leaf level, crop traits, and canopy level, we see again the comparison between traditional hybrid and hybrid with active learning. We see that those solution is the best one and is reliable because it's on-dependent data. We have still some problem in develop leaf level traits, but at the canopy level, the results are absolutely satisfying. So from those algorithms, we can produce maps. And this is an example of the maps we produced last year for winter season, winter crop. The entire farms you can see there. Of course, the reddish area are the ones that are not yet cultivated, correspond to summer crops. But you can appreciate how strong is the variability, the information on the within field variability. And if we say that in details, we can see the phenology changes from the tillering to the flowering, ripening stage for the two crops that we have there, soft wheat on the left and durum wheat on the right. Here we can appreciate. And this is even more appreciable when we go to further to other crop traits, in particular with the canopy chlorophyll content and the canopy nitrogen content. We see that at the end of the season there in May, already the durum wheat was already in the senescence phase, so reduced photosynthetic activity, and already the canopy nitrogen content was already translocating from the plants to the seeds. But if we focus on the middle in April, that is what we want, to produce information that maybe are actionable for precision farming activity. We can see that the pattern that we found and we quantify in terms of crop traits, nitrogen and chlorophyll, have a strong correlation with the soil characteristics that we were available from the maps of the farm. Passing to the other, so we conclude the cycle, the crop cycle. We wanted to see how is the management of the residues by the farm, so not photosynthetic vegetation. In this case, the methods is fully in a machine learning regression framework. We do not have a model that can model the reflectance of crop residues. We can discuss it later, maybe. And we use it that ground data from USGS and appropriate feature extraction methods to highlight from an hyperspectral data which are the features that can be used to retrieve crop residues and in general MPV. And those features are in particular the one that are in 2100 nanometer. We see that in the new generation Sentinel we will have 3 more bands for that broadband spectra. This is the reason because we have to model that feature in order to retrieve information about NPV. And we model that using a continuous removal approach and exponential Gaussian optimization that allow for each of the spectral regions analyzed to have the width, the central wavelength, the depth, and the asymmetry. Using those features in a framework of of machine learning, we use, in particular, that we use random forest. We were able to model, and the results you see there are in cross-validation, and that are pretty good. And the model that we developed with the USGS spectral library were tested with independent data collected in the field and were validating in the picture you see there. We were happy about these results, so we are using this model to making regularly crop residue cover maps, like the one you can see there. We compare that with the information we have in the field, and we can deeply understand how the management of the crop residue is ongoing. Of course, the red area are where the crop is not yet harvested, so we have fully 100% non-photosynthetic vegetation, but we can see also a gradient of the presence of the crop residue there according to the management of the field. So coming to the conclusion, so what we saw is that we can retrieve from Prisma data and map, and in the future we expect it from CHIME and SBG, information on crop traits during the season that can be an added value to support agricultural practices, and to quantify the post-harvest presence of MPV and crop residues. The active learning approach was working very well. We still have problem with leaf level. At canopy level, we are very satisfied about the results. And in particular, the spatio-temporal pattern we saw are exactly in correspondence with what we know in the field and according also to ancillary information. What we saw for crop residue is that it is extremely important to have continuous short-wave information with narrow bands is the only way to retrieve such data. Of course, and this is really a conclusion, the 29 days revisiting or the on-demand that we have of this system that are precursors, so they are doing their work, they allow us to make the algorithm, are not enough for agricultural monitoring. But we expect that the future mission that were described before, also together not only with the Hyperspectral one, but together also with the new generation of multispectral data can be the right way to provide information on crop traits during the season and residue at the end. Okay, thank you.
Thank you, Mirko. And with that, I think we go to the next speaker, who's coming from the University of Massachusetts, so from across the Atlantic. It will be a remote contribution from Paul Sequeira on the Nisar mission, which is another JPL mission on SAR, L-band, and S-band, which I'm looking forward to hear too.
Great. Thank you very much for the introduction, and nice to see everybody in the room. Let's see, hopefully you can see my screen. Yes, you can. Okay, good. Anyways, yeah, you're all welcome to come over, visit me in Massachusetts when you have time. It's nice to, I wish I could be there with you in Frascati at the moment, but we're ending up our semester here at the university. So I'm here to give you a talk on the Nisar, which is a repeat pass LNS band SAR for agriculture and ecological applications. It's one of the next big Earth missions that NASA will be launching in the upcoming months. Let's see. Oh, good. Okay, so this is like a quick overview of what the mission is about. It's a 2-frequency mission, LNS band. Some of the take-home messages here: it has a 12-day repeat pass. It's a science-driven mission, which means we're sort of addressing a number of different applications. And I've got some view graphs to show the sort of large-scale coverage that we'll be having from the that'll be available. We have a 240-kilometer swath or larger, and 6 a.m., 6 p.m. Repeat orbit. And our sort of ground resolution is on the order of 20 meters globally. Let me see here. This is I'm the ecosystems lead for Nisar. So ecosystems is composed of a number of different components. We're doing biomass disturbance, wetlands and inundation, as well as what you might call managed ecosystems, which are agriculture, which I'm the lead of. So one of the things I'm going to be sort of spending a lot of time on is talking about the L-band side of the mission. One of the reasons being is that we'll be having global coverage of L-band. S-band coverage will be complete over India and certain CalVal sites throughout the world, but not in general global coverage. This idea of having a 12-day repeat at L-band means that we can sort of look at how land cover is changing in active time. And agriculture is a great example of that with a 12-day repeat. And we're basically getting 2 observations every 12 days, once on ascending and once on the descending pass. And so we'll be able to sort of watch crops grow throughout the season and look at how things are changing actively. And that'll be a big advantage of what the mission has. To give you an idea of what the observation strategy is, I mean, you can see everything that has a color associated with it will be observed by Nisar at L-band. You might notice that green is one of the dominant colors here, and that's going to be the dual polarized. That's copol H and also crosspol HV received 2 times every 12 days. There are some areas that will be collecting quadpol data, notably in the Midwestern part of the United States and over parts of India. Just to give you a quick overview of optical versus synthetic aperture radar, they're sort of complementary pieces of observation, right? So optical, we're looking at reflectance spectra with sort of like low frequency, what I call L-band SAR with a 24 centimeter wavelength. We're looking more at structures. And hopefully you can sort of notice the complementary nature of things in these images, especially the one on the right. And maybe I'm just very used to looking at SAR images, but you can clearly see where there's agricultural fields, where there's forests, urban areas, and water bodies. And for those of you who aren't fully familiar with SAR observations, this is sort of a quick tutorial, and I just spend a second or two on this. So we're primarily sensitive to things like structure and variations in the dielectric constants of the targets, particularly things related to soil moisture. And so as crops grow, as they're changing their stature, the balance between what you might call surface and volume scattering changes. And this is primarily what we're observing with the instrument. So, reflectivity of the surface is controlled by surface roughness, which is proportional to wavelength, and the dielectric contrast between the air and soil, which is primarily governed by soil moisture. And as mentioned in one of the previous talks, the longer wavelengths that are associated with microwaves have no trouble penetrating through clouds as an active system. So we're sort of making both day and nighttime observations very reliably. So Sentinel-1 is sort of a excellent sensor that's been managed by ESA in quite some number of years now. And so that has it's C-band, it's a 5.5 centimeter wavelength. ALOS and Nisar are 1.2 gigahertz, which is a 24 centimeter wavelength, and actually not listed here is the S-band, which is a 12 centimeter wavelength. So we're sort of fundamentally sensitive to things that are associated with the scales of wavelengths that we're observing. And sort of by contrast, of course, is things like optical spectrum, looking at green light as 500 nanometers, which is much smaller, and one of the reasons that we don't penetrate through clouds. But so by having these longer wavelengths, we're sort of being sensitive to structural characteristics on the order of those wavelengths. So, having a microwave sensor in space, a high-resolution microwave sensor in space, such as Sentinel-1, sort of lets you make large-scale observations of everything on the Earth surface. And this is a good example of some of the products that are created by Sentinel-1, just by doing a false color image of the copole and crosspole, and then the ratio between the two of different land surfaces throughout the world. The color variation here sort of alone gives an idea of the amount of information that's contained within the data. You can also, rather than just looking at sort of static observations of copole and crosspole data, you can look at time series. So by having a reliable time series is a unique information source all by itself. This is Sentinel-1 time series, looking at the average backscatter for copole and crosspole, as well as looking at the variation over time and adding a false color to those things. And you can clearly see the amount of information that's available in these kinds of data sets. South of the Lake Okeechobee there in southern Florida, you can clearly see sugarcane and a wetlands area called the Lochahatchee National Wildlife Refuge, where a lot of the water drains off from the sugarcane fields. And you can sort of see the color self-consistency within the sugarcane, as well as some variation there showing you different statures of the crops that are associated with the region. So you can use this as a fundamental signature, right? So things that are varying a lot in terms of their land cover management, you can clearly see that in agricultural regions. By contrast, things that are urban or forested regions are fairly stable, and open water tends to be very dark at microwave frequencies. And so we can use this as a signature for monitoring active crop area. One way that we've been successful at doing that is by using the coefficient of variation, is looking at the standard deviation of the radar cross-section over time divided by the mean of the radar cross-section over time. It provides this unitless metric that can be used for determining where there's crops and where there are not crops. Here's an area in central India, the state of Madhya Pradesh. On the right-hand side is the glob cover, land cover classification for this particular time, and on the left is the one that was collected from an ALOS time series. If you look closely at an image like this, you can see that there's a lot, in fact, the classification, just looking at the ALOS time series in terms of coefficient of variation, is more accurate than what was provided by glob cover in this case. Something else that you can do is by having a dependable time series, is use the time series for not just determining if there's crop versus non-crop, which is necessary, pre-classification if you're going to do different types of crop classifications that you might have. And so looking at how different crops vary as a function of time is a signature all by itself, and we can use that to good effect. There's a fairly simple algorithm you can create where you just use the time series and you look at how variations are happening within a particular crop type as a function of time of the year and as a function of time. And by using the sort of time series behavior, looking at the variation amongst different crops as a function of time, you can create a land cover classification all by itself. Rather than just sort of being strictly machine learning, this is a flexible approach that can be used as statistically based and can be used for doing crop classification. So we did this in some parts of the United States, and we had an 83% classification accuracy. I'll share you some of the results associated with that. Here's a cropland data layer we have run by the U.S. Department of Agriculture in the United States. Sort of like what you might call the gold standard of crop classification. It's optically based on basically one observation at critical time of the year versus this time series approach that you see down below using L-band UAV SAR, looking at a time series. And this is a pixel level classification. And what you can see, hopefully you can take away from this, is notice the sort of consistency within field boundaries and sort of the fundamental relationship between the top image and the lower one, showing that their classification results are quite good. We did something similar using Sentinel-1. Because of the shorter wavelength, I personally was skeptical at how well the time series approach would work. But again, by comparing the cropland data layer with Sentinel-1 time series, you can see a very good agreement between the two. Again, it's a pixel level classifier, and you can see within field boundaries, it's very self-consistent. And so this was quite successful too. So this kind of work has been published in a number of different journals. You can sort of look these up. Some of the take-home messages are the coefficient of variation is using variation in how the land cover is changing, and also looking at the time series in the one below. There's other papers that are doing this sort of thing, and this is a notable one, a very recent published by the University of Maryland, and Becker Rushev is notable here. And I actually included this one because I like to look at the time series looking at corn or maize versus sunflowers. And you can actually see there's a difference in how these things behave as a function of time and also depending on the time of day. I also happen to enjoy the picture of the sunflowers in this picture. So this is next to my last slide. These are the take-home messages for Nisar. So I didn't mention this earlier. Our current launch date actually was supposed to be in April of this year. There's been a slight delay because of some thermal issues that they're in the process of fixing. So it's currently the best estimate of the launch date is fall of this year, most likely September, early October. One thing that Nisar will provide is a dependable L-band time series, 2 observations every 12 days. There'll be S-band data collection over agricultural cal-val sites, has a high resolution, 20 meters. It's dual polarized. There will be quad pol over Indian parts of the United States. The ground projected data notably will be co-registered to a fixed grid. So doing things like making time series analysis will be very simple, just stacking up images on top of each other. And it'll be available over all land surfaces globally. So fundamentally, this means that it's going to change the way they use data for managed ecosystems like agriculture. There's a lot of data that's being collected. It turns out to be 4.5 terabytes per day. So it's done because that is the sort of amount of data that we're collecting. And so one take-home message you might have is learning how to work in the data in the cloud will be an important skill to develop over time. In other words, bring the algorithms to the data rather than the data downloading to your laptop. Because if you're downloading 4.5 terabytes to your laptop, you're going to be buying a laptop quite often. And this is just a nice little picture of my last slide. So showing you what Nisar looks like. It's a large mission. It's a joint collaboration between India and NASA. And so we're all looking forward to this data being made available soon. Thank you very much for your attention. It's been nice spending this short time with you.
Thanks a lot, Paul, for giving us this outlook for Nisar and how we can use it. I understand you have to log up very fast, so perhaps if we have one fast question in the room, I would like to give the opportunity for that, because he will be not there for the final round of questions. Anybody? Nope. Well, then, Paul, we will collect the questions and come back to you if there's anything.
I'll be very
in
happy
the
to.
final one.
Well, thank you for your time, really. Bye-bye.
Thank you for your contribution.
Okay, so we now moving to the last presentation of this session. If I understand from the title, it will be really a coherent approach from the satellite to the service. So looking also on water management. So Florian, the floor is yours. Well, just if you can try to keep that in certain limit of time would be nice.
Okay. Good afternoon, everyone. It's a true pleasure to be here and present HydroSat and our product AgriWatch. So HydroSat is based in the United States, in Luxembourg, and in the Netherlands. And as mentioned, we're a company working both to build a thermal infrared satellite constellation and to also provide an end-to-end solution of data analytics products making use of that data. The motivation you've already heard and be familiar with. There are more and more people living on Earth. We need to feed them somehow. And, well, with the same or ideally less amount of area and water being used. And we are also under increasing pressure from natural disasters. And at HydroSat, we see ourselves as providing the geospatial intelligence to support this food security, public safety, and also to protect and, well, ideally rebuild the environment. Now, when it comes to thermal infrared, the data sources out there of great quality, but they're either high spatial resolution, and then you wait a week or maybe more for the next image, or you can get daily data, but at resolution where you won't actually see most of the agricultural fields. And our mission is to unlock this power of thermal infrared imagery, really from space, daily, and with a high spatial resolution. We started in October 2020 to test the first ground instrument, which we're actually also flying on a high altitude test balloon. And since then have been building towards launching our first spacecraft, which is actually being shipped to the launch provider now and is targeted for launch in July this year. And the second instrument is also already ready and being integrated, so we're looking forward to having 2 Pathfinder missions in space soon. And then following next year, we'll build up our constellation to reach the final aim. And this is shown here in a bit detail. So the key is we want to provide daily data at a resolution targeting 50 meters ground sampling distance for the thermal infrared with a combined VNIR payload and do that, well, continuously so we can monitor every agricultural relevant place on Earth every day, everywhere in the world. Now, in the meantime, if we want to already provide data analytics products, and we don't have our data yet, we have to have some kind of way to fill the gap. So we're also investigating thermal sharpening routines that, in the meantime, until our full constellation is available, we can already provide and use for our own products high-resolution thermal imagery. And the idea is, well, you have multiple low-resolution images, and if you have a set of high and low-resolution images, you can use information gained there in order to provide a synthetic estimate of how your high-resolution thermal image might look like. It's of course not ideal, but it's better than nothing, and we're eagerly waiting to have actual high-resolution thermal data available from our satellites. But in the meantime, this is the data we're using for our products. Now, having thermal infrared data that opens a huge variety of use cases, and for example, irrigation optimization, which is what we'll be presenting soon, where you can also not only monitor wildfires, you can actually predict wildfire risks by looking at the water cycle. You can do a lot of analytics and drought prediction and disease monitoring and many other use cases. But since we're here talking about agriculture, that's also what I want to be focusing on here. Now, why thermal infrared? I haven't really been talking much about that yet. So really the key differentiator here is that from a thermal infrared satellite, we can measure leaf temperatures, and they reflect the actual subflow through the plant. And now, plants are amazing things. They have a very delicate balance of water potentials that sucks water and nutrients from the soil through the roots, through the stem, and then transpires through the leaves. And just as a human transpiring, this water interaction leads to a change in temperature. So from the satellite, we can see differences in transpiration rate, and that means differences in plant growth based on temperature differences. And the key advantage there is we can detect crop stress from the thermal infrared measurement well before you would see that stress in the reflectance measurement. So even if the leaves are still healthy, green, you wouldn't expect anything is going wrong if you look from a visible near-infrared satellite. In the thermal image, you can already see that something is happening. The second big advantage here is this coupling of the soil water potentials between soil, plant, and atmosphere. So by looking at the transpiration rate, we're actually looking right into the root zone of the crop. So we're not just sensitive to surface soil moistures. We can actually see deep into the soil, and even if the top surface is dry and you might expect you have a problem, you might have enough reserves down below the ground, and the plant might still be healthy. And with thermal infrared, that's exactly what you can see. Now, we did a few studies where we apply this in reality, and well, if you can measure soil moisture in the root zone directly, you can compare it to what you would expect from precipitation data or from a water balance approach, and that way you can actually monitor how much water the farmer has applied. And that becomes incredibly important when we're talking about water allocations, but also, of course, optimization of irrigation, saving water and still producing the same yield. And this is just an example with a local partner where we monitored multiple fields, and you can see that the total amount of water that has been applied from artificial sources is actually monitored quite reliably, purely based on remote sensing techniques. Now, if you look a bit more careful into the plant, it's not just the water you can measure. We can also look, for example, at nitrogen uptake rates. And also there, we see that from remote sensing, we can provide information about the nitrogen content on a plant to a farmer, which means they can now optimize the fertilizer use. And ultimately, of course, the farmer is interested in yield, but if we actually determine all the relevant parameters for crop growth, then we can monitor yield. And we can show that field by field, and this was a test lifting campaign where we compare our results against actual field measurements, where we can see that we can accurately tell the farmer how much he can harvest from any of his fields. Yield is also interesting for us. We talked about ground truth data, and it's very difficult to find spatially resolved ground truth data to compare against. Yield is one of the nice exceptions because the current combine harvesters, they can generate yield maps quite nicely. That's an example here where we see the dry matter production we calculate on the left side, and the actual harvester yields data on the right side. And although we're here working mostly with synthetic sharpened thermal data, we can still see that we get the general trend quite right here, which is a nice thing to be able to do. And that also means that we can show maps of agricultural variables to the farmer, which they don't actually have to do anything. They just have to sign up their fields and see the results. And that's the next key point. Will farmers use satellite data? And the clear answer is no, they won't, if they have to have a PhD in remote sensing to use them. And that's where you need then someone to step in and provide a portal which makes it really, really easy to use. So that's what Hyperspectral IrriWatch is all about. That's our product for irrigation management, which is an online portal where we provide daily field insights at 10-meter pixel resolution for growers, agribusiness, or whoever's interested in that data. So that's a portal where you just need to sign up your field, and you can get a number of parameters on irrigation, on crop, on soil health, on climate conditions for your fields. This is, for example, a sugarcane farm. And here we have the actual evapotranspiration as a layer. So you can just open the portal, look at the actual evapotranspiration. For us, that's interesting. The farmer might say, okay, what is ET? So we can, of course, also show other parameters, like in this case, crop growth. So they can see immediately how much is the crop growing here. And of course, we can go one step further. You can click on a field, and then using weather forecast, we can tell the farmer exactly, okay, this is how much water you would need. That's the rainfall that's expected to happen. So in this case, within, I think this was on the 5th, so within 5 days, you have to irrigate 9 millimeters. And then they simply see how much they have to irrigate, and they don't need to irrigate more because that's enough to keep the crop perfect. Now, the organizers asked to present some R&D recommendations, and I think I did a fairly poor job in putting them concisely on the slide, but let me explain. I think what's holding back a bit this knowledge transfer from the fundamental studies into a product that's easily applicable is, on the one hand, we're not there yet at a mature industry. If you build a computer, you can pick your RAM, your disk, your processor, and there might be incompatibilities, but overall, you'll get a computer that works, most likely. Here, that's not necessarily the case. So for example, this thermal sharpening is important for us. We need land cover classification, crop and soil maps, field boundaries, and it's very difficult to find a data set that's immediately fulfilling the requirements. So we're actually doing most of that work in-house. If everyone has to do that, that's of course not very efficient. And maybe the next point as a key step, when it comes to agriculture, it's a very dynamic environment. We already heard this. The farmer wants to know what's happening in the field right now. If the data is 1 week old, the crop might already be dead. And that's something that needs a bit more, maybe, elaboration, because a crop map doesn't help the farmer much if he gets it at the end of the year. You want a crop map at the beginning of the season. And these are maybe some questions where we can discuss, but I think there should be a bit more focus on what's the actual requirement on the end. And with that, I come to the end. Thank you very much, and I'm very happy to discuss with any of you further.
So we have now, let's say, 10 minutes left to have some questions from you to the speakers, to the single individual presentations, but also, as we just heard, we'd like to hear also your ideas and recommendations, perhaps about how we best can exploit this data, how we can combine them, how we bring that into value for agriculture monitoring. Is there something actually even missing would be the final question if you look at all these different new missions coming up. But I would like to open the floor to you. We have 10 minutes before the next panel, and it's up to you to fill it with information. This one? Just a second, Lauren. So I think we need a microphone for you. It's coming. Sabrina is doing her best. It's over here, Lorenzo.
Oh. It's okay.
Thank you very much. With specific regard to the last presentation, which is clearly precision farming, so to the very fine detail, I'm asking what is the role of the farmer information to the system? Is the farmer providing information on crop yields, for instance, which help to calibrate the model and to improve it? So are we there, or is the role of crop yield data collection still not managed, let's say, within the system, and we need additional processes to gather that data? Thanks.
Yeah, that's a good question. And for operational use, so it's very difficult to get reliable data from the farmer. In principle, some of them are very eager to share data, and that's always nice to have these collaborations, but it's typically something that has to grow. There has to be a common interest, a common trust, and then more and more data is shared, or in the case of field campaigns where there's a specific target of, let's check yields for these fields, and this leads to collaboration where we actually do optimize data for a specific farmer. In most cases, farmers are very busy. They want to spend as little time on computers as possible because they have to do that anyway, and they're very busy. So in most cases, we try to avoid input data from the farmer. The more we can get, the better, but the system has to be robust enough that it can survive wrong inputs, missing inputs, or inputs coming too late. That's what I would say.
It's okay. Straight.
You hear me?
Ben, we have a question here.
We have no, sorry. We had question first here. It was the first one.
Okay, let's, Stefan, we're coming back to you in a second. Okay.
Thank you very much for the floor and thanks for the wonderful presentations. My name is Nancy Marango from Kenya. And I have a question about the user engagement perspective, because most of the times Earth observation data is left possibly at the policy level. Are there any existing systems that can support the users to access the data, use the data, and be able to cross-learn from one region to the other? Thank you.
Okay, could be also. Okay, so thanks, Nancy. You promised me in the coffee break to give me a hard question, so here you go. Yes, it's certainly all the data, at least from the institutional part, will be openly available. So the Sentinel's next generation and expansion missions will be on the cloud. I mean, we heard from Nisar that this is something necessary to bring the algorithm to the data, and not the other way around. So that part, I think we can say we supporting. Then you're saying bringing it to the user. It really depends. I mean, we have one of these interactions here is on the interaction here. We're bringing actually the scientific participants in contact with our policy owners. So there is also that kind of discussion. I mean, just after this session, we will have a panel with our colleagues from FAO talking about how they use it. So we're trying to bring that type of link to the users, and that is a very particular type of user, the FAO and their member states. Nancy, you also, you work mainly in Africa, so there we have the EO Africa initiative, where we have trainings, we have workshops, we have the innovation lab from EO Africa to make sure that there is some use already in preparing the use of thermal data and hyperspectral data in Africa. So there's an R&D program behind it. So there are different levels how we're trying to make this sure. And then I perhaps can even bring that back also to Constel IR if they're still here. Perhaps you have also some idea how to interact with the users. It's perhaps an interaction here as well to have. There's perhaps you can bring the microphone to our Constel IR colleague.
Yes, thank you. That's a great question. At Constellar, we really make a big effort to interact closely with the partners and the customers that we are in, and we really try to take them on a learning curve. So really try to understand what are their use cases and to take them on a learning curve to be able for them to integrate this data that is not straightforward to integrate. So it's really something that we are actively fostering at Constellar, is to really bridge the gap to leverage the full potential of that data also for any type of users.
Great. That is another perspective from the commercial part. And finally, what I was not mentioning, we have the Sentinel User Preparatory Program. There is just a call was closed where we actually invited you as a science community to give proposals how we could use these new missions. And that is also something which we continue to do over the next 1 or 2 years. There will be new calls coming. Stefan, I was stopping you.
No worries. Thanks a lot. I also would like to pose another follow-up question on this calibration, because I think it's really interesting. So it's really interesting what you showed you on this land surface temperature correlation with evapotranspiration and with also predicting then some kind of water stress. I'm not sure to what degree this has been really fully exploited. I mean, there has been a lot of work on soil moisture, global soil moisture products. A lot has gone into that. And I think it's very good that the future missions are actually considering on a higher resolution the land surface temperature. So that's really great also for your application. But I'm still wondering if you could give us a little bit more insight on how you're doing this calibration. I know you're a company, maybe you don't want to tell us everything, but
it's not that straightforward because you have land surface temperature which is dependent on the current temperature you have, and then you have to calculate relative how lower the temperature it is due to some kind of reference, right? Otherwise it won't work. And depending on the stress the plant has, this temperature is less reduced as it would normally be. Maybe you want to say a bit more about it because it is interesting. Thanks.
Yeah, indeed, that's a tough thing to calculate. So our model is mostly based on the surface energy balance model. So we're using the CBAL model, which was invented by one of our now employees. And I would say that has been studied and validated for many decades. The difficulty then is in making it operational, because there's always something you have to tune, and indeed I cannot disclose all of the details and all this fine-tuning. And this also brings us a bit back to the previous question on the validation data and the ground truth data, because that is actually something that has to grow in the field, which is why I think it's the correct thing to have an integrated approach. You have to work on the satellite data, but you also have to work on the applications, because we're now, well, we have close to 2 million hectares signed up on our portal where we run these kind of energy balance processes to predict crop stress and irrigation information, but of course we'll not have enough field data to see whether the result is actually true. So we run validation campaigns, and these were just a few examples I showed. We have more of that data, but it is kind of a fine-tuning. So we start from an energy balance, and we then get feedback from our clients saying, hey, you tell me to irrigate, but I don't think that's true. And then we can go into the data and see, was it maybe an issue with the weather data, which happens quite often actually, or is there something we have to tune on the models? So that's then where, say, our research part comes in. But in principle, it's not much else than what has been developed also in scientific studies before. Maybe the focus a bit more on the daily things. What I mentioned, one of the focus areas, there's a lot of validation on ET models on, let's say, growing season or annual scales or monthly ET values, and that doesn't tell you much about the day-to-day variations. You can do this validation, but you have to really focus on something that's interesting for the farmer.
Okay, and I think we have actually a session on water resource intelligence on Wednesday afternoon, which I think there will be lots of opportunity to discuss this in further. And I think at the next panel there will be Livia from FAO as a land and water scientist sitting. So I think we can also push the question over to our experts in FAO. With that, I think I don't see any other question. I would like to thank my co-chair Michel and thank for your attention, and we hand over to the next panel. Thank you. When you go to the marginal, you turn right. Before you go to okay, that's what I'm afraid that when I arrive to somewhere. But you use in the listing, so you should be. Yes, but they don't know. Yeah. Together. Hand over to you. Thank you.
Yes. I think that we are going to need. To be here, but I mean, yes, please, as you wish. You're okay with it? You're okay with the question, right? You are okay with the question, right?
Yeah.
You're asking the questions finally? No.
I was instructed to... no, but I will moderate the session.
Ah, okay. So you're not giving the keynotes, but you're
Because
moderating.
I was supposed to give the keynote, but I was not supposed to be here in the session as well. So I put the keynote already up, right?
Right.
So
We improvise.
yeah, we improvise. So Neil is do we know anything about Neil?
He went to another organization by mistake.
Which organization?
He went to another and so the guy from the economist, the guy, listen, there's this guy here, but where should he go? So in the best message is out, so it's not here. So I was
Well, maybe we can start. He's the last one.
Okay. Yeah, no, we have to start anyway.
Can you imagine Office of Emergency? That's why.
Hello. We are starting. So can I kindly ask you to go take your seats? Okay, so good afternoon again. My name is José Rosero Moncayo. I'm the Chief Statistician of the Food and Agriculture Organization of United Nations. And you already heard me a little bit early in the afternoon. And as I said during my intervention at that moment, FAO is committed on leveraging Earth observation data for evidence-based decision-making. And in this context, we are proud to host a panel discussion that delves into the transformative potential of Earth observation for addressing the critical challenges confronting agriculture worldwide. And on this, the Food and Agriculture Organization of the United Nations is very well located, okay, I will say. Because from our corporate point of view, we have specific needs given our mandate, in which, of course, we are trying to use Earth observation applications to real daily situations or problems that we have. At the same time, we listen very carefully to our country members that are requesting from us specific issues, okay, that has to do with agriculture, of course, that can be solved with or are under the scope of Earth observation. So what this panel is going to do then is going to use that kind of perspective, right? The user perspective, but at the same time, it will bring together experts that work in FAO that are exploring how Earth observation can inform sustainable agricultural practices amidst mounting environmental, climate, and sociopolitical pressures. We are going to see different themes, okay? Each of the team is going to be presented by a specific expert. The first theme is going to be about monitoring agricultural resources. And in this one, we are going to emphasize FAO's commitment to leveraging Earth observation for monitoring land and water resources, which are critical for sustainable agriculture. As a second theme, we are going to cover adaptive agriculture in climate change, in which we are going to highlight FAO's effort in utilizing Earth observation for crop mapping and developing adaptive strategies to mitigate climate change impacts on agriculture. Then we go to the theme of tackling deforestation drivers. And here we are going to address FAO's role in assessing and tackling drivers of deforestation through Earth observation-based monitoring and analysis. Finally, we are going to cover the theme of assessing impacts of conflicts in agriculture, where we are going to discuss FAO endeavors in assessing the impact of conflict on agriculture using Earth observation data. Having said that, let's go immediately to the presentations, and let me introduce Livia Pelzer. I hope that the pronunciation is okay. She is Senior
and senior land water officer. So she's going to cover the topic of monitoring pressure and agricultural resource base, Earth observation for land and water information systems. Livia, the floor is yours.
Thank you. Good afternoon, everybody. So yes, I'm Livia Peiser. I'm a land and water officer and heading the geospatial unit in the land and water division at FAO. So I'll be mentioning how we work with Earth observation for monitoring the pressure on land and water resources for agriculture. So to do that, we publish regularly. Last edition was 2021, next one will be next year, a book that is called The Status of Land and Water for Food and Agriculture. So I'll just summarize the key message here is that, as we have heard already, that because we need to feed a growing population in 2050, the global agricultural production will need to grow as compared to now for about 35%, and this also means that there's additional between 20 and 30% water use that is going to be used for agriculture. So that means that the pressure on land and water resources is already so high that there are many farming systems and livelihoods that are compromised and that their livelihoods are threatened. So in addition to that, of course, the increase in temperatures is already altering the hydrological cycle and amplifying the pressure on land and water resources for agriculture. So that's what we say in the stages of land and water in our flagship publication, but how does that really look on the ground? So I just take the example of the last country I visited a few weeks ago, but it could be any, basically, country we work with, any of the member countries that Jose just mentioned, and those are the people we need to provide answers to. So in Pakistan, there's already since a few years cycles of droughts and floods. In 2022, there was devastating floods that killed thousands of people, and that came after also devastating droughts that left the soil dry and compacted and amplified the impact of floods. So then when we go to these countries, then we meet at the ministries, and people normally ask FAO support in answering questions such as how do we manage water at times of scarcity, how do we distribute between the different provinces or irrigation systems, or very specific questions such as is it good for us to support increasing apple farming system, apple cultivation in Balochistan? That's a very dry area of the country. Or should we go instead for, I don't know, grapes or olives? And what farming systems are proving to be more sustainable and resilient to climate change? So these are the questions that we need to address, and that's our duty in working with our member countries. So we already use Earth observation to help us addressing these questions. So in the case of Pakistan, for example, and many other countries, we have the vapor database. That's an open access database that monitors land and water productivity, and that means that includes data on actual evapotranspiration in near real time. And by the way, it also provides data on root zone soil moisture, similar to what we heard just now. We call it beta product because it's still a beta product. We are not sure yet of how well it works in different circumstances. And the data is completely open, and there's a Python application that you can use and test it yourself and go and see all the different details in the algorithm. So all our both data and algorithms behind it are open source, and we really welcome people to try it and give us their feedback to help us improving. So in addition, we have the vapor database that can help us address some of these questions. We have detailed land cover and crop type mapping up to 10 meters that can, for example, we can see what is screenshot here is exactly apple orchards in Balochistan, so we can see how much water are these orchards already consuming, and what's the trend in the recent years, how much they are impacting on groundwater resources. And we also have a database and tools like the global agroecological zones that we can use for deriving suitability assessment under different climate and management scenarios. So we are well positioned in a sense, but you know very well that doing these things takes a lot of time, resources, and capacities. So we have almost 200 member countries in FAO, and with a growing pressure, we cannot address all these questions alone. And I conclude, and this is the last slide, by saying that we cannot do this alone. We need your help. We need the help of this community. We have already a very good collaboration with the European Space Agency through the Memorandum of Understanding that was mentioned earlier. We have less formal, but still good collaborations with many of the partners here, like GEOGLAM or the Global Land Monitoring Service, which we use data and we provide our inputs to what type of data would be useful. Of course, we work with CGR, with research and academia, with the private sector. So we need to strengthen these collaborations, and we need, and this is probably the R&D recommendation in our point of view, we need open data, methodologies, and tools. In terms of data, of course, we are very much interested and looking forward to use the LSTM data and also the precursor data when that is available. We need global actual ET. We do provide through the Vapor portal at the moment global actual ET at 300 meter in near real time. But as I said, this takes resources and that could be used in different ways by FAO with really more direct support to our member countries. So we really hope that in the longer term, this global type of operational data can be taken up by partners. We need crop type mapping, irrigation mapping, phenology, but not in a scattered or project-based type of settings, but on an operational and longer-term perspective so that we can build the capacity with countries, we can institutionalize these products with our member countries. We've been successfully working with European Space Agency and their initiatives being champion users, so-called, and through that we can contribute to our user requirements and develop together use cases, so there's a good example of that. We've been like the ET for FAO, the workover, war serial. Through that we also shared our reference data that were used in these initiatives. We're very much interested, and FAO is also working with ESA on defining data interoperability, like the stack or cloud optimized GeoTIFF. So what technologies with our IT department, there's also this stream of collaboration. And overall we need, and we can provide stronger country engagement because that's something that is very much needed, and FAO can play a role in that. So with that, I'll stop. I just wanted to ask you to reach out to us. There's a pretty big team of FAO experts in the room and coming in the next few days. So please reach out to us. There will be, just as a teaser, one presentation on Vapor tomorrow morning, and then a poster on Wednesday afternoon. And another presentation on how we use Earth observation for food security monitoring in Afghanistan on Tuesday at 12, and a poster on the global agroecological zoning again on Wednesday. So there will be opportunities for discussing in detail. Thank you.
Thanks, Livia. Now we move to the second theme, that is adaptive agriculture in climate change. And we are going to hear from Lorenzo Di Simone. He is a geospatial technical advisor in FAO. and he will be presenting about crop mapping and crop yield process-based models for adaptive agriculture in the face of climate change. You have the floor, Lorenzo.
Thank you. Good afternoon. And we've been hearing a lot about the need for agriculture to satisfy growing needs for production, to meet population future needs. And of course, this can happen through two essential approaches, either through increasing the crop yield or either increasing the crop production area of both. But we know that increasing crop production area then has an impact on ecosystem services, on gas emission. So today we're just going to focus on crop yield increase. So of course, this depends by the capacity to reach the crop yield potential. In this context, timely assessment of where are the crops and how much the crop are producing is essential. In official statistic terms, so we refer to crop yield and crop acreage. FAO is supporting countries in actually modernizing their national statistics offices, in particular using Earth observation big data, in line with the recommendation of the data revolution underpinning the 2030 agenda and the SDG framework. So Earth observation data are expected to provide a series of advantages for the use of agricultural statistics. So first of all, they're expected to allow to have early estimates compared to official statistics. Secondly, they allow for higher degree of disaggregation. And they can help to increase the accuracy of area estimation when they're used in conjunction with field data. So there is an efficiency by the use of Earth observation data at low cost. And finally, Earth observation data can be used to improve survey design, so to improve the current protocols used by countries to collect data in the ground, so that less data is collected, but it's collected better in a much more representative way. This said, FAO is responding to this need for the modernization of agricultural statistics through the EOStat initiative, which was launched in 2019, actively implemented in 21 countries. And it focuses on several technical activities through active capacity building. So crop type mapping, crop yield forecasting, automatic field boundary delineation, optimization of survey design, and best practices in georeferencing. So many of the activities that have been already mentioned by other colleagues today. We work in 21 countries, as mentioned, upon country request, country prioritization, countries that are under the priority list of the end-in-end initiative of FAO. So there are different criteria. I just would like to mention on the key aspect of the work, which I think are the most relevant ones. The first one is the engagement. So it's fundamental to engage with the National Statistics Office and the ministry that are concerned with official statistics to understand which are the current protocol for data collection, to discuss with them their expectation from Earth observation data, to understand if there are gaps in the current field data collection systems, and then, of course, co-designing and co-implementing pilots and validating together solutions and have official endorsement of the country of the method, of the results, and the recommendations. For the crop type mapping, of course, we strongly advise for supervised approaches, so approaches that then lead to validation. In doing this, we have strong collaboration with the University of Louvain and the European Space Agency. We use a lot the Send4Stat approach, which many of you will be familiar. And the activity really articulates over the reaching in situ data existing already in the country through official protocols or with ad hoc survey, and evaluating also the fitness of those protocols for the use of Earth observation data, validation, system deployment, and of course this depends also on the data sharing intention of the country. So some countries want a local deployment, some other countries are okay with the cloud deployment. And the advantage of the Send4Stat in a nutshell is really the low complexity, the robustness, and the sustainability. We also, okay, this is a national map in Senegal that was produced in 2018, has been updated in 2021, and now we're expecting a new baseline in 2024. The other activities is the crop yield mapping, and essentially crop yield forecasting and mapping using crop growth models, which allow us to actually model the crop response to the daily inputs, such as the solar radiance, precipitation, temperature, and the crop growth model, the process-based model, allows us to simulate the soil plant atmosphere systems, which allows us to have pixel level prediction. Essentially, we can run the model on a pixel level. And the way we essentially use this model in collaboration with the Michigan State University is by collecting crop statistics time series from the country at national level, at district level, sometimes at crop cut level. We integrate this with geospatial explicit information about the crop type maps, about soil, precipitation, temperature, and then the data is fetched to the SALUS model. And then this model then finally forecasts the yield within a range of conditions, so the normal conditions, wet conditions, or dry conditions. And of course, the advantage of this type of approach is that we can model the crop yield in a spatially explicit manner. We can consider the influence of the season, so the current season, and we can predict also outside of the range of data that we give to the model, because it's run based on the fluxes of nutrients and the water cycle inside, let's say, the plant atmosphere soil system. In this case, it's an example of the prediction for Cameroon for corn for 2 different years, 2005, 2010. This is an example of crop prediction for rice for Cameroon. What I want to add is that, so how does this come to adaptive agriculture? So because we use this type of models, then we can ingest into the models climate anomalies data, which allow us to understand what happens, what is the crop response in the country in 5 years, in 10 years, under specific anomalies. And essentially, the country is able to understand in this way that by increasing, for instance, the maximum average temperature or the minimum average temperature, the crop yield is going to be always lower and lower. So they need to start thinking about other cultivars which are more resilient and adaptive. And in this context, Earth observation data allows us essentially to provide information for enhanced decision making, because we have knowledge of where are the crops, what are the yields, so we can improve the risk mitigation and planning, so the use of fertilizers, the use of water, optimize supply chain management, support for policy and assurance program. So I think we are at a really good time where the wealth of data availability and the wealth of machine learning and models now allow us to have more seasonal monitoring of both crop yields and crop acreage. Thank you.
Thank you, Lorenzo. Now we move to the third theme in which we are going to talk about deforestation. And for this, let me give the floor to Anne Bradholm. She's a forestry officer in FAO, and she will be speaking about assessing and tackling drivers of deforestation. Anne, you have the floor.
Thanks a lot. I know it has been a long afternoon, almost there. I think you have still 2 presentations left. I know that the concentration might be a bit out. So I'm going to talk to you about another topic, which is, I would say, a bit outside of what we talked earlier about forest. But you will see that it's not so different as a topic. So what about the pressure on forest? As you know, deforestation is a big concern. It's a challenge for all. The world lost in the past 20 years 100 million hectares of forest, despite of the key role those plays in a number of topics like livelihoods of rural and urban population, for biodiversity. Forest hosts 80% of the biodiversity of the terrestrial land. In the water cycle, so it's closely linked to agriculture. If forests are gone, there is no water. And also in mitigating climate change. Though there are some evidence that deforestation is slowing down, and I think that's a good news. In the past 10 years, we have observed that the deforestation is now getting to a level of 10 million hectares per year. Good news, bad news, it's an improvement. So I think let's continue. And how to halt this deforestation? How can Earth observation imagery and data can support halting deforestation? We need a better understanding of the deforestation drivers. This is key to design innovative solutions and to halt and reverse forest loss. That's why we need to take advantage of the new remote sensing methods and data to obtain adjusted, updated, fine-tuned information on land use change dynamic. FAO, as part of the Global Forest Use Assessment, FRA 2020, carried out a remote sensing survey. It's not something new, it's something that we have been doing every 5 to 10 years for the past let's say 30 years. But of course, now technology is improving, so we have better tools, better data, and these help us in this duty of monitoring the forest worldwide. So this FRA 2020 remote sensing survey was about studying the forest changes in 2 periods, 2000-2010, 2010-2018, using a sample-based approach. So it's a constellation of 400,000 samples all over the world, for which we had samples of Earth observation data from Landsat and Sentinel 2. And I would say the big strength of the approach was to involve local experts. So we have been involving more than 800 national experts from 126 countries. And this is really the asset of this exercise, how we can include the field knowledge into the interpretation and the analysis of satellite imagery. It has been a 1-year process, and we have found that agricultural expansion accounted for almost 90% of deforestation worldwide, even more than what we were expecting before. 50% of the deforestation during this period of 2000 and 2018 were linked to cropland expansion, almost half of it, and 38.5% was linked to the expansion for livestock grazing. As other drivers that were monitored, we have also urban and infrastructure development, which accounted for 6% of the deforestation worldwide, and some changes in the water, dam construction in the water, which accounted for almost 2%. Alone, oil palm plantation accounted for 7% of the deforestation worldwide. Of course, this 88.1% of forest converted to agriculture hides a number of situations. So we have done a further analysis of these drivers of deforestation by looking how much of the land, of the forest converted to croplands or grassland was converted due to small-scale farming or large-scale farming. In large-scale farming, it's not only the extent of the areas that we're looking at, but we are looking also at understanding which are the investment, which is the scale of investment that are put in terms of machinery, infrastructure, put into the land for this conversion. The result of this analysis showed that 68% of the global agricultural-driven deforestation was associated to small-scale farming. Alone, 71% of the conversion of forests to cropland was due to small-scale farming, and 64% of the livestock grazing into forest was also linked to small-scale farming. This suggests really to emphasize, to strengthen the efforts in addressing the weaknesses of the current production systems when designing strategies against deforestation, and to consider not only the conversion, but also all the concomitant needs, including food security, decent income, and secure tenure rights. Therefore, the study findings can support more tailored policy making. We have also made some special studies on understanding the drivers of forest losses in some special forest ecosystems, the mangroves, which are very important for livelihood also. And we found out, using the same approach, using sample-based area estimators and 21,000 samples all over the world of the mangroves forest. And we found out that 27% of the mangroves were lost due to agriculture, but also that 26% of the mangroves were lost due to natural regression. And this is also linked to climate change. Other key drivers of those loss were rice cultivation and oil palm for about 8%. So these are an example on how we use satellite imagery to provide the global information on the trends of forest. We are currently proceeding with the next remote sensing survey of forest cover changes, and we are this week launching the FRA 2025 remote sensing survey. It is based on the same approach, on the same samples, so it's an update of the previous FRA 2020 remote sensing survey, but we are adding another date, 2023, so we will be able to monitor also the change in the last 5 years. We have an optimized sampling design. We're also adding some imagery on that, some as particular planet data. And we're also adding variables to analyze the drivers of forest dynamics, and in particular to identify the specific crops, pastoral systems, and disturbances. I will conclude by showing you also some example of FAO work for halting deforestation by forging positive solutions and managing trade-offs. We are working in 3 main workflows, enhancing the synergies between agriculture and forestry, notably in the context of small-scale farming, which can be linked also to international supply chains. We are also mobilizing resources at scale to address the challenge of deforestation and forest degradation, including climate finance and residue-based finance. And last, we are also working on sustainable management of forests, in particular for climate, by directly benefiting local community and enhancing forest carbon stock. All these activities imply multiple engagement from different stakeholders and data. Earth observation data are, of course, really core, and we are also supporting countries in developing national forest monitoring system. And I will end here this presentation. These are a few publications that you can download directly from the FAO Global Forest Resource Assessment website. And I would like to thank you for your attention.
Thank you, Anne. And now we go to our final presentation. This is going to be on the theme of assessing impacts of conflict on agriculture. So let me invite Neil Marshall to take the floor. He's a senior technical officer on the Office of Emergency and Resilience in FAO, and he will present on Earth observation for the assessment of the impact of war on agriculture in Ukraine. Neil, you have the floor.
Thank you very much. Thank you very much for that. I work in the emergencies division of FAO, and I actually created an emergency for myself by arriving at the wrong train station. So you would have seen me rather hurriedly take the stage. So I'm really living the job, if you like. Anyway, it's great to be here. I want to talk about the work that we've done in the emergency division with Lorenzo and his team in the context of the war in Ukraine. Specifically, we were trying to understand. We've used remote sensing quite a bit in the context of the conflict over the last few years. But this particular use was related to the Kakhovka Dam breach, which you're all aware of, no doubt. And I'm going to be taking you through what we did to try and understand the impact of that dam breach on agriculture. Okay, so just a bit of context. The Kakhovka Reservoir and irrigation networks, actually before the dam breach, were serving irrigation needs in 8,000 hectares of irrigated cropland. It's a huge area. That was enough, the actual production on that cropland in 2021 was 2 million metric tons of grain and oilseeds. And the grain produced was enough to feed 8 to 10 million people for a year. So truly enormous quantities of grain being produced on that, in that area. The reservoir itself accounted for about 13% of the total fish catch in Ukraine in the year 2021. So very, very significant provision of fish, therefore incomes to the fishermen, etc., etc. So 4 oblasts were affected in this dam breach. The irrigated areas of 4 oblasts were affected. These 4 oblasts together make up about 25% of all cultivated land in Ukraine. So hugely important for Ukraine, and as you know, Ukraine is a net, a rather large food exporter. So these oblasts are very, very important. Particularly important, this is actually, I mean, in a sense, now we're talking about occupied and non-occupied parts of these oblasts, accounting for about 40% of the winter barley grown in Ukraine and about 20% of all harvested production in the country. So really significant in terms of agricultural production. Now looking at the disaster context, the destruction of this dam, which happened on the 6th of June last year, created a huge crisis, generally. And we were charged in the emergency division in trying to understand the impact on agriculture and agricultural livelihoods as a result of that dam breach. So it was very difficult to do this because in other cases we would send people out into the field to do some field observations and interview people and drive around, etc. But obviously it's an active conflict zone, so that was not possible. We could not move around, and there was also a lot of data confidentiality. Any data that was collected in any means had to be agreed with the Ukrainian government before anything could be done with it. We couldn't do any field missions. We couldn't do any ground truthing. We did do some interviewing of what's called key informants. We went to some of the villages which were just inside on the Ukrainian side, the non-occupied side of the border, and we did do some interviewing, but it wasn't. It didn't yield much information, and of course there was no information at all from the Russian-controlled side. So in that set of circumstances, how do you calculate the agricultural impact? That was the big question. What everyone thought originally was that the impact of the actual dam breach was so dramatic. Huge wave running down the Dnipro River, sweeping everything before it, knocking out villages and infrastructure, bringing lots of debris with it. Everyone was focusing on the downstream from the dam breach, and I'll show you exactly where it's been breached in a minute. So we were actually involved to try and understand the impact on agriculture of of the dam breach. So you can see here, there's a pink, oh, there we go. There's a, oh, where do I point it? I'm obviously not doing it very quickly. There's a green dot up there, you can probably see. That's where the dam was breached. And all the red was the flooded land, the flooded cropland. So that was looked at, and what we found there was that, and that was using satellite imagery very effectively to understand this. And there's quite a lot of damaged cropland, but in terms of overall damage to agriculture, it was relatively modest. Then attention turned after the initial shock to looking at the real impacts, which were on irrigation. So this is where we worked very much with Lorenzo and his team. Oops, something's happened. I don't quite know what's going on. Maybe it's some interference from a foreign, I don't know. Anyway, I'll keep talking. I think we're okay. So you can see where that sort of star is, that's where the dam breach was. And you can see on this, the green sort of area, the green lines are actually the irrigation network running off this river and also the dam itself. So you can see that most of the irrigation network is actually to the east of the Dnipro River, and basically the dam itself and the estuary and the reservoir was irrigating most of Crimea, which is actually now under the control, as you know, of Russia. But also there were various other parts of the irrigation network going into other oblasts, which were more under the control of Ukraine. And what we tried to do then is to look at the impact of the dam breach on these irrigated areas to really understand what the impact would be actually on crop yields and crop production, particularly in terms of grain crops, oil seeds, other things. So as you can see on the right-hand side there, we did some high-resolution imagery we got hold of some high-resolution imagery from Maxar to see the before and after effect on the mouth of the North Crimean Canal. The North Crimean Canal is the one that comes off just below the star, and you can see very clearly that it's dried out almost over 2 weeks. It's completely dried. So the decline in water was rapid. The reservoir was basically empty within a few weeks. So we were charged with looking at this, trying to understand this in terms of its impact. So what was done was that with Lorenzo and his team, we took a look at the irrigation networks in all of these 4 oblasts that you can see on the screen. And over the course of a number of weeks, this analysis was done. So there were many challenges in undertaking this analysis, especially from an emergency response perspective, and that's the field that I work in. Because it was a localized, although it was huge, it was a localized disaster occurring within a larger ongoing conflict. So the impacts of conflict had already heavily affected agricultural activities. So we carried out what's called a post-disaster needs assessment, and we had to try and isolate the impact of the dam breach specifically on agriculture and try and separate that out from the ongoing, or if you like, the underlying impacts that already were occurring before the dam was breached. So we had a very short time period for analysis. We had to basically worked very, very fast in a period of about 6 weeks. So that involved a lot of late nights working to try and understand the impacts, using techniques of Lorenzo and his team. The other problem that we had is, this incident is very close to the front line. And in fact, I was going to show a map of the front line. Basically, it hasn't really changed much over the last year. It's basically most of the areas east of the Dnipro River are under Russian control, and that hasn't really changed. We had really real issues, in getting, the information and being able to show it, because it had to be agreed with the Ukrainian government. So this took a lot of negotiations and discussions as well. We had a lack of baseline information, and the irrigation map that I showed you was very outdated. We had a very short time frame for analysis and drafting, 6 weeks. So all of these things constrained the analysis. But these are normal things for emergency work. And I think in this kind of context, remote sensing and Earth observation have a massive role to play in allowing us to assess the impact on agriculture and both in terms of production and impacts on livelihoods of smallholders. So these are the challenges. What are these? Yes, here we go. What are the successes? I think a big success was the geospatial analysis in and of itself, which was an essential tool, and it's becoming an essential tool in all conflict settings, in fact. And we're using it now in the context of Gaza, and we're also using it in other conflict settings in the Sahel. And it's extremely useful to fill data gaps. It was a great collaboration between 2 divisions in FAO, and it used a multidisciplinary team in the context of scarce data to get information out in very tight deadlines. So what was the final result? The final result was this publication, Post-Disaster Needs Assessment, which is a joint publication between the World Bank, the EU, and the UN. We were in charge of the agricultural sector analysis, and we were able to estimate through these techniques the losses in terms of losses occurring through lack of production, or production, essentially no production or very low production. And we give that a dollar value. So you can see here on the in the table here about 373 million US dollars was the value of the losses in terms of what happened with the dam. This is very significant because in order to recover from that, a lot of money is needed to actually recover from that. Obviously, rebuilding the irrigation networks. I mean, essentially, the only recovery will be when the reservoir fills up. Well, one thing to recognise about these figures here, these are annual figures. So basically, this is 368 million a year, 370 million a year that's being lost here. So it's huge amounts of money. I think I finished there. Thank you very much. Yeah, that's it. Thank you.
Thank you, Neil, and thank you as well to Livia, Lorenzo, and Anna to show us the variety of topics that FAO has to cover. And of course, it also exemplifies the need of the insights that we need from the Earth observation community. So let me jump immediately to the part that we take questions from the audience. I think that we have some minutes, probably 10 minutes, if we stretch it a little bit, in order to take questions directly from the floor. So I guess that someone will help us with the microphones, right? I see already 2 hands, one here, one there.
Yes, please. Can you introduce yourself and also to indicate if the question is to a single expert that is here or is it a general question? Go ahead, please.
Thank you very much. My name is Nancy Marangu from Kenya, and I have two questions for Anne and the gentleman inspects who presented before her. And my first question to Anne, she had a presentation that highlighted on the challenges, and one of the challenges was disturbances. I'll appreciate if she can expound more. What did she mean by the disturbances? And secondly, the question to the gentleman is, you spoke about using survey design, and I'm happy to learn from you within different countries and different contexts. Do you employ a standardized survey design, or what metrics informs the use and the employment of the design? Thank you.
Thank you, Nancy. We are going to take more questions, please.
Thank you. Thank you. My name is Mario Zappacosta. I'm from FAO, and I lead the Global Information and Early Warning System on food and agriculture. And I would like to stress something that Neil put in his presentation at the end that may look trivial, but it's definitely not. So a multidisciplinary approach, because, I am an economist, and today, since, 1 o'clock, I heard so many technical things that are telling me Earth observation for food security. But we have to work a lot on the linkage between what the scientists are doing and what we have to put in place. Some of the information should be able to digest and to understand. If sometimes, maybe we need a third actor between the producers of the information and us, that are at the bottom, that we have to understand what is the message. But when we work in a multidisciplinary approach and we are able to work together, I think this is the way that we can make, more than papers on highly specialized journals, and make it, useful for the people working on the ground. Over.
Thank you. Is there any other question, please? We can take one more question. Yes.
Hi, my name is Anna Szeniszewska, and I represent CABI. I have a question to Lorenzo as well about the EO for agriculture, related to the crop modeling, helping to improve country level or subnational level crop production statistics. I'm wondering what are the learnings so far, or how promising it is at this stage. I'm wondering what's the match or mismatch between the statistics that you are receiving from ministries of agriculture compared to when you are trying to validate it with the models, or is the statistics helping you to calibrate the models? Thank you.
Thank you very much. I see no more questions, so we go. Let me give the floor first to Anna.
Okay, thank you very much for the question. Okay, disturbances is not that easy question at the end, as I talked to you about deforestation, which is a conversion of forest to other land use. But what about the disturbances in the forest? So the degradation or the disturbances. And this is not really an easy topic. And I think we are far from being able to monitor really the forest degradation. But what we will try to capture is a few of these disturbances, especially due to fire, due also to logging activities, logging for wood, logging for charcoal consumption or wood energy, and disturbances also because of some events like natural events such as pest disease and storms. So we will try to capture why at some point forests can be unstocked or with a lower stock by adding a few variables on that. Thank you. I hope it answers your question.
Thank you, Anna. Lorenzo?
Thank you. So the question was regarding the survey design. So depending on the country, so the first assessment is really understanding what is the protocol in place if there is an annual agricultural survey, for instance, and what are the measures, what is the design, and how fit is that for geospatial work. So are the samples well distributed per class, per geographic area, and what is the georeferencing? Is the household georeferenced or is the parcel georeferenced? So based on that, we're able to formulate recommendations and eventually implement in the field an experimental and adjusted survey to show the different results. In the case instead where there is no agricultural survey official process, for instance the case of Zimbabwe, then we start from scratch. So we resort to Earth observation data in the actual design of the area frame, so we can construct an area frame based on geospatial variables, for instance agricultural intensity, and then we use traditional statistical approach like Cochrane's formula in order to understand how many samples we should collect for each strata for a given accuracy that we're expecting by the end of the classification process. So yes, we use standardized approach, which is stratified approach, random sampling, and Cochrane's formula to compute the total number of samples. Thank you.
Thank you, Lorenzo. Neil, there was not in reality a question, okay, that Mario did, was more to complement what you said. But I have a question for you that is more about how do you see basically this type of work, okay, leveraging of Earth observation to try to assess the impact of conflict? How do you see that being scaled up, okay? And more importantly for this community, which type of insights or collaborations do you see coming from this community?
Thanks very much for the question. Thanks very much for the question. I think there's a huge potential in this area, linking these exciting techniques with a real understanding of the impact of conflict on agriculture and agricultural livelihoods. It's really helping us, and just to step back a bit, I mean, there's a very clear relationship between conflict and climate as well. I mean, you know, you tend to find, and there's increasing numbers of studies on this, the relationship between, you know, climate drivers of conflict, and, you know, there's an important interaction here. Where there isn't that interaction so much, it's still incredibly important because what it allows us to do as emergency responders, it allows us to get real knowledge of what's happening in an area where there's no access. So, for example, Gaza is a good example. Now, many people may not be aware that, in fact, before the conflict in Gaza, the population were more or less self-sufficient in a number of products, number of things that are necessary for food security. And by looking at using remote sensing techniques to understand the impact on various things such as agricultural land, agricultural greenhouses, access to feed for livestock, etc. Also, of course, access to fishing and damage to ports. We're really able to get a really good understanding of the impact of the conflict on agriculture. It enables us to prioritize response types. It enables us to share with the world what's actually happening in a very compelling way. So I think that, you know, the more these techniques evolve, the more they're able to be specific, Particularly for us, I think, in terms of things like crop type monitoring as well is very, very important for us in these situations. I think the better our responses will be, the better they'll be, essentially. So, I think I can only sort of raise my support to strengthening the partnership in this area. I mean, Mario knows we're working with his team and NASA Harvest on understanding the impact of the El Nino drought in Southern Africa. I know it's not conflict, but it's another example of that. It's also being used in the context of Somalia, which is obviously an unstable area, to understand the impact of flooding. So I think there's a huge potential, and I think we in FAO, especially in the Emergency and Resilience Division, would really welcome partnership with technical colleagues who can help us get a better handle on this. Thank you.
Thank you, Neil. And now let me go back to Lorenzo, because it seems that he forgot to answer a question. So very quickly.
There was a question from Anna about the modeling of crops at subnational level and the match with official statistics, and whether if official statistics are helping to improve the estimates. So indeed, the capacity of Earth observation-based crop acreage assessment, they match quite well with official statistics. Whereas crop yield models based on statistical models that use Earth observation data as inputs, like leaf area index or NDVI, those type of regression-based models are a bit weaker. So the regression is not really giving good results. So this is why we resort to more complex modeling, which is the process-based model. However, in process-based model, we don't really have one figure. We have a kind of a variety of ranges of attainable yields, depending on the different development of the season. But when we pre-train a model using, for example, 10 years of data, and then we backcast for 5 years, so we have countries where we have 15, 20 years of data, like Ecuador, for instance. So when we do the backcasting, then the model is very, very well mimicking the official statistics for those years that were not used for the training, and it can understand the anomalies in the climate and the impact. So it is much more reliable. Is statistics improving the efficiency of Earth observation data and vice versa? I would just say that it's been demonstrated now. We have figures that show that when Earth observation variables are integrated with field survey data for the estimation of area, crop area, then the coefficient of variation of the estimator diminishes. So there is an increase of accuracy when you introduce Earth observation data, which means that if you wanted to achieve the same result using survey data, you should intensify the sampling, and that would come with a higher cost than using Earth observation data. Of course, Earth observation data don't come for free, because you need resources to use them, even if they are free data. So, thanks.
Thank you, Lorenzo. And just let me finish with Libya, okay? So there was no question for you. I will make a question to you. And let me go back to the issue of partnerships. In your presentation, you mentioned, okay, a few examples of fruitful collaboration between FAO and the European Space Agency. How do you think that we can leverage this for a greater impact?
Thank you. I'll keep it very short, because the poster and icebreaker is waiting for us. So I'll just, refer back to one of the examples I made. So there was, we are happy to partner with the European Space Agency. For example, we did that through the ET4FAO initiative, which then contributed on one hand to an improvement of the vapor database in its version 3, because we used some of the thermal sharpening procedures that were developed under the SEN-ET framework. On the other hand, that's contributed to, we hope, soon a new global evapotranspiration product being added to the Copernicus portfolio. So that's a very good example. We need more of that. And of course, we cannot expect that Copernicus takes up every every good initiative or that ESA produces or suggests. So we need more partners. We need to maybe combine efforts for finding new resources and also finding ways of engaging the private sector. That is still, I mean, as we always repeat that, it remains a bit tricky for an organization like FAO and for others, I guess. But we need to find new ways of doing that for bringing this up to scale. So thank you, and back to you.
No, thank you, Livia. And with this, I think that we can close this this panel. Can we please thank all the panelists? And thank you as well, all of you. This has been an opportunity for FAO to be able to show you how we are using Earth observation and its potential in order to address critical challenges that are confronting agriculture worldwide. So I look forward for the next days of this workshop, because of course we will have the opportunity to interact with all of you, the community, and learn from you and try to even put the next round of collaborations and partnerships. Thank you very much and have a good day.